Go notation. This week we are going to start looking at the data structures themselves, and we are going to be starting with arrays and strings. So just a bit of housekeeping. While I'm giving the presentation, if anybody has a question, you can just drop it in the chat. I will be monitoring the chat as we are going on, and I'll be trying to answer questions. I'm of the opinion that it's better concepts are clarified on the spot. So if you have a question, it's better to ask it right away, because it's easier to assimilate further things if your doubts are clarified early. So also, I also want to appeal to everybody. After the session, survey is going to go out. Please ensure you fill that survey accurately and give feedback, any type of feedback, constructive feedback, destructive feedback, please. We need that to improve on the quality of the program, and also to get feedback from you guys, because as we are teaching, it's not just we just giving information. We also have to make sure that people receiving the information are satisfied with what they are getting. So please ensure that that format, endeavor as much as possible to fill it, and be honest as possible. It's anonymous, nobody sees any information about you. So the main aim is just for us to get feedback from the program. So if there's something the tutor said you don't like, say it. If there's something the tutor that is doing well that you want them to continue doing, say it. So yeah. So today I'll be very mindful of our time. Last week we went overboard. So today I'm just going to dive straight in, and yeah. Okay, so let me share my screen and make it a slideshow. Okay, so is my screen visible to everybody? Okay.
Yes.
Perfect. Okay, so let's dive right in. So what are we going to be talking about today? We're going to be talking about a couple of things. We are going to start with the memory organization. So I'm going to first give a lecture, like a presentation, and I'll talk about arrays, and then we'll look at solving problems later on. So I'm going to talk about memory organization. We're going to start with how things are stored in memory at the fundamental level, which is on bit and byte level. Then we're going to move a higher step up in the abstraction to primitive types. Primitive types are kind of the lowest level of abstraction that is available to we as programmers. And from there, we move on to the RAM model of computation. So the RAM model of computation is a way to help programmers view the system, and it just helps us model the system so that we can focus on writing efficient programs. Then we start talking about arrays. Arrays is the first data structure we'll talk about, and it builds up on the primitive types. Then we'll talk about strings. Strings and arrays are kind of the same thing. So once you understand arrays, you understand strings. You just have to be careful because strings have some nuances to them depending on the programming language you're using. I believe we are being recorded. Can you confirm? Okay, yes, we are being recorded. So let me just put it. Okay. So the other thing we're going to be talking about, I'm going to be talking about patterns. Because of our time, we'll not be able to go through all the patterns, but I'll list the patterns. I'll go through a few of them, do some problem solving on some of the patterns, and yeah. Then I'll give some exercises that we can try to next week, and then I'll share a couple of resources that will help us improve. So the aim of this program is my aim right here is to go to the next slide. Yeah. So my major aim here is to help you build your intuition. We can't cover everything about the data structures that we are to cover in this program. That is not what we are trying to do. I'm just trying to help you build your intuition so that it's easier for you to keep learning on your own. Yeah. So just a bit about me. You met me last week, so we don't need to go over all this, and let's dive right in. So for memory organization, how are things stored in memory? So let's take a trip back to the memory lane. Recall last week, I talked about the program execution model. So when a user writes a program, he's sitting down with the disk somewhere on the user system. You double click the program or you run the program, the OS loads it into RAM, and the CPU fetches the program from RAM. And there's a back and forth between the CPU and RAM during the program execution. So the key thing to note here is all data structures we're talking about in this course are created and stored in the memory, which is around during the program execution. So arrays, strings, all of them, they are stored in the RAM. So how is the RAM organized? How is memory organized? So at its core, right, we all know that computers store data in zeros and ones. Now, but memory is accessed at the byte level. It's not accessed at the bit level. So the unit of access to memory is 1 byte. And 1 byte is 8 bits. And so you can kind of view the memory as a sequential arrangement of bytes. So let me give an example. When we say we have 4 gigs of RAM, what we really mean is that we have about 4 million bytes of RAM. And that really means that we have about 4 million addressable slots of 1 byte each. The same thing applies to 8 gig, just that we have 8 million addressable slots of 1 byte each. So it's important to understand that memory is accessed on a byte level. So for those of you that are low-level programmers, you know that if you want to actually manage memory yourself, you have to manage it on a byte level. You can't access it on a bit level. So that's one thing I wanted to clarify here. So now we know what happens to our programs when we run. We know where they're stored, and we know basically how the memory organizes things. So now let's dive into the basic storage, which is the primitive type, the basic storage of primitive types. So the primitive types are different for different languages, but generally, you can categorize them into 2 parts. Numbers, which are your ints, your longs, your floats, your doubles, and you have strings, so characters. Character is just basically anything that is text, any string. So strings are anything that is text, and strings are made up of characters. So a character is just a character like a, comma, space, and that usually takes 1 byte. Now there are exceptions to this, but generally this is what you have in all programming languages. So these are the atomic units of storage, and every other data structure we'll consider in this course, they all build upon this. So let me start with how numbers are stored. So let's take an integer. An integer is 4 bytes in most languages. Some languages larger, some languages smaller. So if you write 4 bytes in binary, that's 32 bits. You have that sequence in binary. The sequence here, you have this sequence here in binary. Now, since memory is accessed at the byte level, this is a sample representation in memory. So the memory is accessed at the byte level. But one thing to consider is that every memory location has an address. And so I denoted the addresses with a pound sign here. So if I use pound going forward, just know I'm talking about the addresses. So this is kind of a visualization of how 4 can be stored in memory. So it starts at memory position 4. So normally the operating system and the memory manager determines how all this happens. You don't really need to do all these things, but it's just good to know how they are stored so that you can build your mental model. So you have this stored in memory like this. So it starts at a particular location, and each location is a byte, and then it stores it together because it's 4 bytes. So all other data types, longs, floats, all other numbers, they follow the same pattern, except that if it's 4 bytes, it takes 4 locations. If it's 8 bytes, it takes 8 locations. If it's 12 bytes, it takes 12 locations. But the fundamental thing is they are stored together in memory, depending on the size of the data you're storing. So some languages have more types, some languages have fewer types, but it's still the same concept. 2 bytes, 4 bytes, 6 bytes, whatever. What about strings? So I'll talk about strings. So essentially, just to answer your question, strings are composed of characters, and characters are mapped to numbers using an encoding. Sorry, characters are mapped to bits using an encoding, and those bits are stored in memory. So let me go now to the next slide. So this is storage of a character. Now, the reason why I differentiated this is ultimately characters are mapped to numbers, but the thing is that's not really entirely correct, because we know that we need to encode the character as a 1 or a 0. So let's say I have a string of 5 characters. We treat each of those characters individually and encode them we have to encode them into bits using a mechanism. So there are different encoding schemes that exist. The most popular is UTF-8 and ASCII. You have UTF-16, you have UTF-32, and but for UTF-8 and ASCII, for instance, A is encoded as that number. So A is encoded as 65. So if you do a conversion of a character to an integer, it's actually 65. For C programmers, you know that you can convert between characters and numbers easily. So that's essentially how characters are stored. So it will take that byte. In this case, it's 1 byte. Some encoding schemes use 2 bytes per character. Some use 3 bytes. Some use 2 bytes. Some use 4 bytes. But at its base level, we don't really care about that. We just want to know. We just need to know that they are stored in memory somehow, and they need to be encoded by a certain rule. And that encoding scheme is what determines what it is. Now, the most important thing is whatever I use to encode it is what you use to decode it. It doesn't really matter whatever you use. Just make sure what you're encoding and what you're decoding is the same thing. So this is how characters are stored. And it's important because a string is just an array of characters together. So once you can store a character, we can store any string and we can store any text in memory. So we're done with the storage. I just want to clarify a point too as well. Like, okay, we'll go on ahead for that. So there's something you come across. I just wanted to include it here for completeness. It's called the RAM model of computation. So essentially, it's an abstraction, and this is something you see that comes up often again and again and again. Someone raised their hand. Do you have a question?
Yeah, I do have a question.
Okay, go ahead.
Yeah, you made mention of in UTF-8 A being 65 or 64. Now, how does it relate to bytes? Because bytes are only zeros and ones.
Yeah. So A is encoded as 65. And if we treat 65 as a number, we can encode 65 easily. We can convert 65 to bits, sorry. So we can write 65 in decimal and convert it to binary. And that is essentially what I have here. So once we can get anything to be represented as a number,
65 and then to binary.
To binary, yes. Yes.
Okay, thank you.
So the key thing here is, and this is something you see over and over again, is the concept of abstraction. We just need to be able to encode this something as a representation of a number. And because we can always convert numbers to binary easily, we are done. You will see this even in colors when you have RGB representing it from 0 to 255. They are using numbers to represent them because they can easily encode them in bits. So you see this pattern forming up anywhere. Whenever you want to encode something that is not numeric, if you can find a formula to convert it to a numeric structure, then you can encode it easily. Yeah. Okay, someone has a question. Go for it.
So my question is, if we have characters being mapped to numbers, and then colors being mapped to numbers, special characters being mapped to numbers, are we going to, is there ever going to be a time where there'll be like a clash, like a character or a color being mapped to the same number? And then if that happens, how does the computer interpret or differentiate between those two?
Okay, so the computer doesn't differentiate between anything. The programmer knows what they supply. So the computer's job is just to give you back what you gave it. So if you gave it a number to store, it gives you back that number. How you interpret that number is up to you in your program. So the programmer implementing that thing knows the rule they used. In this case, so let's say it's an encoding, right? And you encode A as 65. When you get it back from the computer, you know that, okay, you got 65 back. I know that number is back to A. So the context of whatever you are storing in the computer is not known to the computer. The context is with the person storing it in the computer, if that makes sense.
I think I understood her question. I was about to re-explain her question.
Okay.
Yeah, she was asking, okay, everything is mapped out to binary numbers. Is there any time that computers have clash in storage? Let's say A having the same number with C, or you understand? I think that's what's her question. If I'm correct, you can identify.
Okay. So if I get your question correctly, you are saying your question is whether two things could map to the same number, correct?
Yes, yes.
So that is taken by the encoding scheme. The encoding scheme you are using will ensure that that number represents one entity alone. So for instance, 65 is A. If you decode it in ASCII, for instance, 65 is A, and A is 65. If you decode 65 back, you can't get B because the rules of ASCII tells you that that's how it's encoded. So essentially, the point I'm just trying to say is the computer is just like the memory is just a layout. It doesn't know what you're storing in it. It's the person retrieving items from memory that knows the meaning of what they stored. Yeah. So a string for no strings are not 4 bytes. Integers are 4 bytes in most languages. Strings can be any size. A character is usually a byte, and a string. So if you have a string of 20 characters, usually that means 1 byte. There are exceptions depending on how many bytes you use to encode the character. So let's say I have a string of 5 numbers, like let's say a space boy, that's like 5 characters, right? So depending on how I use the encoding, if I encode 1 character to 2 bytes, then the string is going to be 10 bytes. If I encode 1 character to 1 byte, the string is going to be 5 bytes. We will have 265. No, you cannot have 265s. The encoding scheme determines the rules, and depending on those rules, they are stored in memory. When you retrieve them back from memory, the memory doesn't know the meaning of what you assigned. It just gives you back what you stored. So the program retrieving that knows the difference. Linda say like we will have 265. No, we cannot have 265s. So before I move forward, I think there's a bit of confusion here. I just want to know if anybody has any other question before we move forward, because it's important to understand this module before we go forward. Okay, go for it, please.
All right. So, sorry, my question is about the computer understanding these different encoding schemes, right? The UTF and the ASCII. So, is it possible to have a program that have both encoding scheme inside the same program? Can it differentiate? Yes. Or if I'm just running on ASCII, I just proceed on ASCII, or if I want to use UTF, I'll just proceed on that.
So within a program, you can encode it in different ways within the same program. What just matters is the program knowing how to interpret what it has encoded.
All right.
Yeah.
And there's no clash at any point, right?
No. All the encoding schemes ensure that there's no clash.
All right, fine.
Yeah. So again, I just want to reiterate. The memory manager itself doesn't really care about what you store in it. It just gets the byte you store and it stores it. When your program requires those bytes back, it gives your program back. Now, what those bytes mean is up to your program to interpret. Yeah.
That makes sense.
Okay. Thank you. So if you have any question, please feel free to ask. If I'm not clarifying it, feel free to ask again. Yes, Afiz, you have a question? Go for it.
Yes. Hi. Good afternoon. It's my first time here, Shay. Okay. So just want to ask about when you have a string, right? The same string, and then you convert it into a byte array, and then just want to do a kind of reverse. I know for some reason, when you print out the byte array, that you see the different kind of characters. I mean, see it printed out in a different form, not having the same letters or so. But when you are converting back to the string, then it converts it back to the same string for you. So just want to know why is that when you are printing out, for example, you convert, let's say, Ajah to a byte array, and then so you print it out, it gives you, it's provided the byte array for you. If you convert the same thing to array and byte array again, it's going to print out a different bytes for you. But when you are converting to a string, so you get the same value. So can you explain more about that? Why is that so?
Okay, so if I get your question correctly, you are saying sometimes when you print the byte representation of the same string, you get different byte representations, correct?
Yes, that's correct.
Okay, so in that case, without getting more context into the programming language you are using, and which programming language is this, by the
way? Java.
Okay, so again, the thing is, there are different encoding schemes that are being used, and if you get different results with the same encoding scheme, then I'll be bothered. But I don't know if it's the same encoding scheme you are using each time. So what's
yes, same character sets encoding scheme.
Same character set encoding scheme, and you get different representations anytime you print it to a string.
Exactly. When you are printing the byte array. So, but when you converting that same binary, byte array to you are converting it back to a string, then you get the same value, even though the two bytes have the different representations.
That's interesting. We can continue discussing this later, but what I'm suspecting is we need to take a look at what encoding scheme Java uses to encode strings, and what particular encoding scheme you are using. So maybe that encoding scheme defines the rules that way. I'm not entirely sure, but we can continue after the lecture, and I would take a look at it later on in Slack to see what encoding scheme is used and why that is happening. Encryption, not encoding. Okay, so maybe, but it said encoding, so I will assume it's encoding for now. But yeah, we can take a look at this later. Okay, any other questions here? All right. So let's move on to the RAM model of computation. So the RAM model of computation is essentially an abstraction, and this is just to make it easy for us programmers to reason about memory and CPU. Because in reality, memory and CPU operations are very complicated under the hood. But usually for programmers, we just assume that we can access any memory slots in O of 1. And O of 1 means it's a constant operation. So we can access any memory slot in O of 1. In reality, it's not really O of 1. I think it's O of root n or thereabouts. But for the sake of the RAM model of computation and for the sake of us as programmers, just understanding the system and building programs, we assume that we can access any memory slot in O of 1. And primitive operations, all the primitive operations are also O of 1. Now, for loops and while loops are complex operations because the loops contain other statements within them. So in that case, they need to be analyzed in terms of the primitive operations they contain. Functions are also complex operations that need to be analyzed in terms of the primitive operations they contain. So based on these four parameters here, we can analyze the complexity of any program, because essentially, if you look at programs and break them down, they're essentially functions, they're a collection of functions and variables. Even looking at object-oriented programming, it's a collection of variables and functions. So if you can break down a function and the function is complex, then we can essentially break down any program. So that's what the RAM model of computation is. But essentially, what you need to understand here is CPU memory access is complicated, and we don't need to deal with those complexities when writing programs. Sometimes they kind of creep up, but I'll explain that as we go forward. So the reason why I'm saying this is there's a scenario we'll see in the future where it's important to know how these things work under the hood. But I'll clarify that. They don't come up a lot of times. Okay, so any questions so far on what we've done before we move into arrays? All right. So let's go into arrays, our first data structure. Why do we have arrays? So whenever you're learning data structure, think about a few things. Why do we have this? Why was it created? What is it trying to solve? Why do we have this? What's it trying to solve? What are the properties of this data structure? This will help you really understand data structure. So the reason why we have arrays are this. If we want to group items together, we already know we can have variables that refer to items. Like we have different variables to get different access to data, pointing to different primitive types. But the issue here is if I want to store a list of things, let's say I want to store 100 names of students, or I want to store 100 numbers. right? Instead of me having 100 variables, I can use one variable to refer to all of them. And this is essentially why we have arrays. It helps us organize data efficiently. And there are three key properties of arrays I want to take into consideration. The first thing is that they store items together in memory. The second thing is that they only store elements of the same type. The third is that they have a fixed size after creation, and that size cannot be extended. Now, I will take a few slides to talk about these properties and why these properties exist, and what they mean in terms of how we carry out operations on an array. So the first thing is arrays store items together in memory. And an array has indices and elements. The indices are what we use to access the elements. So if you look at the visual there, we have like an array of, so if I have an array of say 5 elements, which I created on this line, what happens is we have indices, and the indices start from 0. And this is something that shows people off a lot. In computer science, generally, we start counting from 0. And so if you look at it, A of 0 just means that you're accessing the first element in the array, which is 1. And those indices can go on and on and on to the last element. So this pictorial is how an array is stored together in memory. I'm going to take an abstraction up. Just know that one of those integers stored in memory is actually not 1 slot. It's taking 4 slots in reality. But I'm just going to show it as taking 1 slot, because an integer is usually 4 bytes. And if you are storing an array of 4 integers, then we are taking 16. Array of 5 integers, then we are taking 20 bytes. But here I'm just going to remove that level of abstraction and make it easy for us to visualize. The key thing is to remember is that they are stored in memory, and they are stored together in memory. And there's a reason why they are stored together in memory. It's very important for arrays. So the indices are used to access the elements in O of 1 time. And this is essentially an important property because arrays are very fast in terms of accessing elements. And that is what distinguishes arrays generally from other structures. Indices themselves are not stored in memory, and they are only used to determine how to get the elements. So the key here is that the elements of an array are of the same type. So if I have an array of integers, that array can only store integers. If I have an array of floats, that array can only store floats. If I have an array of characters, that array can only store characters. I know folks that are more into like dynamic languages where you don't really have type, will kind of say, okay, but I can store different types in one, but I'll get to that. But just know that at a fundamental level, an array in a computer, like it can't store elements that are of different types. Essentially, long story short, what those things do is they have like an abstraction to make it look like they are storing elements of different types, but actually under the hood, they are storing elements of the same type. I'll explain later. So why is this possible? Why is this important? It's important because we need to be able to determine the next element without storing information about its location. So think about it like this. If I want to store a group of elements, I have 2 choices, right? I could store them together in the same place, or I could store them in different places. But if I store them in different places, I have to put information I have to encode information about their location in different places. But if I store them together, I don't need to encode that information. So it saves us space, not having to store information about where each individual item in the array is located. Once we know the start of array, we can get any item in the array in constant time. Another thing is it's efficient for caching because it stores items together. I'll explain more on this later. But the key thing to note is this: once the beginning of an array is known, any elements in that array can be found in constant time. And this is a key important property of arrays. So the other thing, so continuing to the previous property, all the elements can be gotten quickly in constant time, like I said earlier. And there's a formula to calculate this. Essentially, it's the base location. The base location, that's the address of the start of the array, plus the index you're looking for times the size of the type. So let's say I have an array of 4 integers, and the first item is stored in memory location 0. Integers are 4 bytes, and the base location is 0 in this case. That means we can find the element at index 120. which is the 125th element because of the off by one, and it's something you should take into consideration when using arrays. There's an off by one mapping between the index and the actual element, the index and the actual position of the element. So index 120 will store the 121st element in the array. Index 0 will store the first element in the array, like that. So we can easily get the element at index 120 by doing this math here. And we know that this is at location 480. So we can just jump there and return it in constant time. The element at index 1, which is the second element, will be at position 4 because the first element will be at position 0 at memory location 4. And so note here that it's the same computation no matter how big the index is. So even if you are looking for index 1 million, you are still going to do one computation and you can jump there easily. So this is why accessing any element in the array is O of 1. And it's important to understand this before we move forward. Okay, so before I continue, do we have any questions so far on what I've explained? Okay, please go forward, Godswill.
Okay, sorry to take you back, but I was hoping that you would. I was hoping you would touch on there was one of the properties of an array that you mentioned in the previous slide, that the size of the array is immutable, which means that you cannot change, right?
Sorry, I haven't finished talking about the properties. I've only talked about the first two properties. So I've talked about the first one and the second one. The third one is ahead, but I just wanted to make sure we get this before I go to that because that's a little bit more involved.
All right, no
so
problem.
I will still get to that. Yeah, thanks for pointing that out. That's very important. Thank you. Let me see what's on the queue. Steven, you're next.
Yeah. Okay. My question is first. The small maths that you placed here is it's when you know the index of the item you're looking for in an array, right?
Correct.
Okay, not when you are looping through the array.
Okay.
No. Second question is how do we even interpret the memory address? Because if I print out let's say I'm writing Go, if I print out the memory address, it's actually 0 times 00 EF blah 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 blah. If I want to, yeah.
So that memory address you have is in hexadecimal. It's essentially a number in hexadecimal. That's the long story short. But it's also, but the thing is, languages also create abstractions that take away these complexities from you. So unless you are really working with C or C++, you might not really get what you think you get because the language has done something. But in terms of Go should be comparable to C and C++ because it compares directly to your underlying platform. So essentially, that number you are seeing is a hexadecimal number. And in this case, I use an example that starts from 0, but in reality, it doesn't start from 0. It starts from some number in memory. There are more details about the stack and the heap and all that I don't really want to get into now because they don't directly relate to arrays. We'll talk about that later when we are talking about stack and stuff. So that's why you see that number. It's essentially OX is a hexadecimal number. So if you take that number and do a hexadecimal conversion, you will get the position in memory. And if you can take an array and store and read the number in Go, I don't know if Go can do that, and read the address of the second element, and you take a difference, it should be the size of whatever you're storing in there. Okay, next question. Does that clarify your question too before I move forward?
Yeah, thank you.
Okay, thank you. Isioma, you're next.
Okay, thank you. I didn't quite get what you said about I don't know if there's a relationship between the memory location of an element and its size and the whole base location thing. I didn't get that explanation. Maybe you want to explain further or recap or something. Thank you.
Okay. So arrays are stored together. That's one fundamental thing. And the array has a base location. The base location is the index in memory, is the address in memory of where the first item of the array is stored. So if arrays are stored together and I know the where the first element is stored and they have the same type and size, I can know the location of where any element is stored by multiplying the size of what I'm storing by the index I'm looking for and adding it to the base location. Does that clarify?
Yeah, it does. I've been working with arrays for a long time, but I never knew that. So
Okay.
thank you.
Okay, perfect. Henry, you're next. The formula on the slide simply shows the location and memory of the element. Yes. It shows it. Okay, go on.
Okay, yeah. So, like, just to be clear, the formula on the screen now just simply shows location of the particular element in memory, right?
Correct. So it shows the location that you find that index in memory. Okay, let me see.
Okay, so that means that we don't really have to bother about the exact location and all that.
So this is just to help you understand arrays. In practicality, you don't really bother about this unless you are working in C++.
Okay.
Yeah.
Okay.
Yeah. So let me see. Let me go back to the queue. Here is our call queue. Okay, I think everybody's hands is down. Okay, I think our queue is clear. Okay. So somebody puts in the message, I'm kind of lost though. Naz, you're lost. Okay. Can you let us know where you're lost so that we can recap it? I know it's a bit difficult if it's the first time you are hearing about it, but just take your time. Like, it's fine. Just take your time and try and understand each of them. Understand each of them little by little. Everything at it, giving you all this information at once, if you're just hearing about it for the first time, can be difficult sometimes. But yeah, you can ask questions in the Slack if it's not something that we can discuss here. So I have to raise hands. Okay. John. Hello, John. Okay.
Can you hear me?
Hello, John. Can you hear us?
Yeah, I can hear you. If you can
you
hear
have
me.
A question?
Yeah.
Do
It's
you have a
not
question?
more. Yeah.
Okay.
No, not. It's out of context here. I want to ask if you can get the link to the recorded class, if it's possible to get the link to the recorded class for those of us that want to go through it again.
Yeah, the organizers will share that link with you. I think you dropped your email when you registered, they will share it to your email.
All right, thank you.
Yeah. So Ifeanyi, you're next.
Okay, hi Shay. A quick one, yeah. So I kind of understand how to like get the memory location of the elements, but I just want to ask, like, where does it come in play in real time development?
So it comes into play for you understanding how arrays work under the hood, and it's important to understand that to understand other data structures. If you are developing in like an interpreted language like maybe Python or JavaScript, you probably don't care about this. If you are working in C++, you don't care about this. So it depends on where you're working on the stack. But we just need to go over it to understand the data structures of algorithms in depth.
All right, thank you very much.
Yeah. Please, once your questions have been answered, please just put down your hand so that we can know who has questions next in the queue, and it just helps us organize things more efficiently. So I'm going to go through the chart. We multiply. So we don't always multiply by 4. It's just because integers are 4 bytes. If we're dealing with floats, we multiply by whatever. So if we're dealing with doubles, we multiply by 8 bytes. It just depends on the size, what the size of the type you're storing is. That's what you multiply by. That's why I said size of type. Yeah. But in this case, it's an integer, so that's why I multiply by 4 bytes. Yeah. So now I talked about something. Felix, you have a question?
Yeah, good evening, good afternoon.
Yeah,
So
yeah, good
I just
afternoon.
want to clarify something from this formula that we have here in getting was it the location in memory for that particular element. Now, if we're looking at for instance, like what we have here, we have an array of 4 that is the size is 4, right? Now, if, for instance, we are getting the location of maybe element 2 and we have a value, then if we're getting the location of element 3, is there a kind of a range that those two will be so that you know that the next one might also be in that range? Or would there be a difference? Or maybe when I get 2, I know that the next one, the location might be, the value might be this, like a range in getting the value.
Okay. I think your question is, once I get the index of where the location, once I get the index of where the value is stored, how do I know what range contains that value? Is that a question?
Yeah, the question is that if, for instance, like this, the elements at index 120, we are going to get the 121st element that we calculated for the 121st element will be at use this formula, you got 480. Then if you want to get the next one, the location in memory, what would be the difference? That's the very next one, considering the size of the array. For instance, like you have 4 here now, 1, 2, 3, 4. You got the one for location 2 in memory, the value given to you. Then you are getting the location of 3. That's the very next element to that one you got. What would be the range so that if I'm getting for 4, I'll know that the difference would be maybe like you got 480 here, maybe the next one, maybe what should be the difference?
Oh, I see.
Maybe a unique thing.
Okay. So if you have an index, if you want to get the location of the next index, you just add the size of the type you're storing. So in this case, you just add 4 bytes. So in this case, index 120 is at 480. Index 121 will be at 484. Index 122 will be at 488, like that.
Okay.
Yeah. So you add the size of the type to know the next index. But the reason why we do this math is because we want to be able to jump to any index quickly. We don't have to start from the first and start adding to find the index we are going to, because that's taking too much time. We want to jump to any index we want. Base location is stored in memory, yes. Your base location is what you store in your array, yes. So when you say array A equals to something, essentially it stores that base location. Okay, so let me go to the charts. 1 second, let me go to the charts. An array of strings will multiply by what? An array of strings, will get to that. But essentially, an array of strings is an array of pointers. And pointers are the same size depending on your system. Yes. So, Isioma, you have a question? Or you?
Yes, just to be clear, is the base location, seeing that arrays, the index of arrays always begin from 0, can we say that the base location of every array will always be 0?
So the base location here is 0 for simplicity. The base location is whatever the operating system assigns to where your array is stored. So typically, when you store a variable, you request the operating system, okay, I want to store a variable. The operating system will give you somewhere to store it. That is your base location. It could be 1 million and something, because usually it's a very large value in hexadecimal. But I just use 0 here just to illustrate the concept, to make it clear. But whatever the base location is, the memory of the operating system handles that. You don't usually handle that.
So as a follow-up on that, if I want to find out the base location for my array, how do I go in a language such as Java? Is there a formula to get it or something?
With Java, it's a bit difficult, I think. I'm not a Java expert here, but if it's still C++, you can easily get it. I think with Go, you might be able to easily get it. But Java, Python, they do a lot of abstractions for you. So because they manage memory for you somehow with a different layer, with the JVM. So what you probably get is what the JVM thinks it is, and it's a bit muddled up. You might not be able to get the exact location in Java. Yeah.
All right, thank you.
You can get it in Python and JavaScript. Okay. Someone says you can get it in Python and JavaScript. Okay, that's good. Then if you can get it in Python and JavaScript, yeah. Okay, so I will move on now. So essentially, the major advantage array has by storing items together is something that is a bit nuanced. So typically, between the operating system, between the CPU and the memory, there's a cache. And the cache helps us to access data quickly. So the idea of the cache is to speed up access because the cache is usually located on the CPU itself. It's not on the memory. But typically when the operating system fetches data to the cache, it's fetching it in blocks. So if your cache line is 4 kilobytes, which is 4096 bytes, if you fetch at an item in memory, it fetches 496 bytes in a chunk. So where this is important is because arrays store things together. If you try to look through an array and you access the first element, it loads 496 bytes from that first element into memory, based on our example here. And when you're accessing the second element, it just goes to cache. So it makes it very easy to look up stuff. That is one key importance and advantage of arrays storing things together. So next week we'll see linked list, and we'll see that linked lists are a bit different. And because they don't store things together, the performances can be very funny at times. So this is called spatial locality. It's something in computer science where data is stored together in a program. But that's aside. I just wanted to include it just for completeness. Okay, so properties of an array. An array size cannot be changed after creation. And this is the last important property. So why is that? It has to be stored together because of what we've gone over. And so what if? So the thing is, if we need to be able to resize an array, it's not easy right off the bat on what to do. Please, if you're not asking a question, can you mute your...
All right.
Oh. Okay, thank you. Please, if you're not asking questions, let's mute our mic so that we can make the experience good for everybody. Thank you. So the thing is, if we have so let me give an example now. If you have an array, say A is 1, 2, 3, and we store it in memory. Now, we store the array in memory. If we want to add something to the array, all right, because we need to store it together, we don't know what is in the next location after the last element. In this case, something is there, so we can't just store it there. So this is the reason why arrays typically can be changed after creation, because they have to be stored together, and because you have to store them together, you have to get space that is big enough to store all those items together. If you need to add another item, you are not sure whether the next space is used or not. So you can't just add it. You can't just add an item to the array. So this is an important point to note in arrays, that the array itself cannot be changed. But we have dynamic arrays. So how do dynamic arrays work? We'll talk about this later. So like I said earlier, we have static arrays, which is what we've considered up till now. Now I'm going to go into dynamic arrays. Essentially, it's an array that can be resized, but it's kind of an illusion, because in reality, it's an abstraction over a static array. So what you have is, there's an abstraction over a static array that copies the static array to a new location. So another static array that is bigger than the previous one, with enough space to hold what you want to store. That's essentially what dynamic arrays do under the hood. But again, if we need to copy items when we want to store items, then that leads to some performance problems. But there are ways you can alleviate this. I'll explain further. So, given an example now, let's say we have an integer array of 1, 2, 3, and these are memory layouts. We have a character and we have a float. Now, if I want to add 4 to the array, because something is occupied, I'm not sure whether it's occupied or not. Now I have to copy everything to a new location and point to that location. So here we can see that we've copied it to a new location in memory. Where that location is, we don't know. The memory system, the operating system handles that. But that new location will be big enough to contain 4 integers, which is what we have here. Now, but there's an issue. copying an array is O of n because it's you have to go through the beginning to the end to copy the whole array. And so if you keep copying an array each time you want to add an element, that will be O of n to add an element instead of O of 1. So we need to make this O of 1 somehow. Okay, so before I go into analysis, do we understand this concept of dynamic arrays, copying to a new location big enough to hold the new array? Someone has their hands raised.
So it was a mistake. I wanted to do thumbs up.
You wanted to thumbs up. Okay. So we are going to go over now to dynamic arrays and how we are able to ensure constant time with dynamic arrays. Please just explain again how it is O of n. So if you want to copy an array, it's O of n because you have to start from the beginning of the array to the end of the array. So you need to go through every element and copy every element one by one, which is the size. So that will be bounded by the size of the array, which is n in this case. So that's O of n. Okay. Now for dynamic, so for dynamic arrays, now I'm going to go through an example here. So if we have an integer 1, so in this case, I think I'll have to pull up like a board. Let me know if you guys can see this. 1 second. I want to share like a whiteboard I can write on just to explain this better. Okay. Okay. So can you guys see? Can you see the screen I'm sharing?
Yes.
Okay, good. So so let's say someone has a question. Okay. So let's say I have an array, right, which is 1. This array is 1. Now I want to add, let's say I want to add 2 to the array. Now I need to copy this array to a new location now and have 1 and 2. This I'm adding 2. Now if I want to add 3 to this same array, I need to copy this again. 1, 2, 3. If I want to add 4, is the writing big enough for you guys to see? Okay.
Yeah, we can see it.
So we need to copy this, which will be 1, 2, 3, 4. So the problem here is because we are copying the array each time. We are doing too much work. So let's say I add 16 items. What's the amount of work I do here? So there are 2 components to the work. You have the amount of work I do due to adding the 16 items, which is essentially n. But each time I copy the array, I double it. I increase the array by 1. So essentially, the first time I do my copy, I'll copy it once. The second time I'll copy 2 elements. The third time I'll copy 3 elements. First time 4 elements up to n. Do you guys remember what this formula is? We talked about it last week. This is essentially n into n plus 1 over 2, which is n squared. So to add n elements, right, it costs me n squared with this approach of just copying each time I want to add an element. So that means to add 1 element, right, it will cost me n squared over n, which is n. And this is bad. So do you guys follow with what I just explained? Or is it still confusing? Thumbs up if it's good, thumbs down if it's not. Okay. So for the thumbs down, can you ask your question so that we can clarify? Someone has a question. Prince, you have a question?
Yeah. Thank you very much.
Yeah.
So my question is that
No, last week I got to know about this during this week. I actually missed out. I believe reason I needed clarity on this because I missed that last week question, last week class on the time complexity thing. So I really know my question is how is there way I can get the video of it so that I don't have to maybe go through it later at the end of the class today because I from what you just said I get to understand that it's very very foundational to this. Yeah, that's my question.
So please reach out to the organizers to get the link to the slide because it was shared last week. Reach out to the organizers, please. They will share it with you. Thank you. For you that for folks that don't understand it, so the reason why it's n squared is because each time I add an element, I have to copy the array. Each time I add an element, I have to copy the array, and that is to copy the array is O of n. So if I want to add n elements, and to add one element is n, that means to add n element to be n squared. So if you don't understand the detailed analysis I've done, just look at it that way. In terms of deletion, no, you don't need to copy during deletion. You don't need to copy during deletion. So usually we care about expanding. We don't really care about reducing. Reducing is to reduce an array, you just delete the item you want and don't use it. But to add items to the array, you need to get more memory. You need to expand it and you need to expand the storage you are using. But to delete it, just remove what you don't need. You don't need to resize the array if you don't want to. So just like you look, yes, essentially just like you look. What makes O of n squared bad? What makes it bad? Can you clarify what the question is? What makes O of n bad? So O of n is bad because each time you want to add an array, you need to copy all the elements in the array to a new location. And O of n is not good each time we want to access an array because we might want to access 1 million elements in the array. So that will give us n squared. And if you recall from last week, when we have n squared, it's not good. It's slow. Essentially, it's slow. Yeah, that's why it's not good. Yeah. So if you missed last week, please watch last week. It's very important. It's very foundational to this. Good. So do we understand why adding a constant each time we are copying the arrays of n to add each element? Okay. Seems folks are okay. If you're not okay, please ask your question. Okay, cool. So now, Stephen, you have a question.
Yeah. Okay. My question is about garbage collection. If it's changing the address where it's saved, don't like in C# and in Golang we have garbage collections that actually wipe off these things. So is it going to still affect the performance if the garbage collection is going to act on it?
So the garbage collector only garbage collects items in memory that are no longer in use. And for you to be adding items to something is still in use. So in this case, it will not be garbage collected unless you release it back to the system. So garbage collection only works on memory that is no longer in use, not memory that you are still using. That clarifies.
Okay, but like you said, that when an array is added, like dynamic arrays, it copies to a new address. It means that the old address is released, isn't it? Or is it still used?
I see what you mean. Yes. So the old address is released. Yep. And it can be garbage collected. Yes. The old address can be garbage collected.
Thank you.
Okay. So I see. So I'll move now to why the optimization we use to make this fast. So the trick here is each time you copy the array, instead of copying it by 1 or by constant factor, double it or triple it. So let me go through an analysis. If we have, I think I should slide show this, okay, because this is the best one. So we have an array that is of size 1. Please follow this carefully, it's very important. If you add 2, we see that there's no space to store this one. Now we need to copy to a new array. But what we do is, because this array is of size 1, of length 1, we double it. So we copy it to a space that can hold an array of 2 integers, and then we add 2. Now we want to add 3. There's no space, right? So we copy it to a new array that can hold 4 integers because we currently have 2 integers. And we add 3. So if you notice, there's an extra space here that is not being used. Now, when we add 4, we don't need to copy again because we already have an extra space here that is not being used. Now, let me continue. Now, when we add 5, we double the existing space to hold 8 integers when we copy it. So we add 5, but we still have 3 slots here that can hold more integers. So when we add 6, we don't need to do anything. When we add 7, we don't need to do anything. When we add 8, we don't need to do anything. When we add 9, then we need to double it again. So the trick is, whenever you are doing a copy, double it, multiply by something. That's instead of adding by something, multiply by something. And the reason why that works is because if you look at all the amount of work we are doing by doubling the array. So let's say we have n equals to 16, now we add 16 elements. If you look at the amount of work we are doing, each time we do the copy, we notice that to add 16 elements, we do like n amount of work, which is 16 in this case. But each time we add an element, we are doubling. So the first time we double, we copy 1 element. The second time we double, we copy 2 elements. The third time we double, we copy 4 elements. The first time we double, 8 elements. So do you guys remember this pattern here? When you have this summation multiplied by 2. Remember, it's O of n from last week. Yeah. So because essentially, yeah, exactly. So this is O of n from last week. So if to add n elements, you do O of n work. That means to add 1 element on average is O of 1. But the trick here is that it's not O of 1 for every element. It's O of 1 for most of the elements. And for a few elements that are unlucky, it's O of n. But that cost is not enough to still change the time complexity. So that's why we have O of 1 here. And we call it amortized. But what they essentially mean is it's O of 1 on average. If you take all the work you do and you average it out, it's O of 1. Is this clear? Thumbs up if it's clear, thumbs down if it's not. Thumbs up as they are coming slowly. They're not as fast as before. It seems this is not very clear. Okay, I was quite fast. Okay. Thumbs down are coming. Okay, cool. Okay, so let's go back. But do we understand the concept of doubling each time we want to expand the array? Do we understand that concept? Do we understand that concept of doubling each time we want to expand the array? Thumbs up if you do, thumbs down if you don't. Okay, so I'll go back.
I have a problem with that doubling, sir.
Okay.
We are doubling, expecting that there would be a later time where we might need to add something to the array again, right?
Correct. And that later time we don't need to double, we don't need to copy again. We just add it in constant time.
And what if there is later, not a later time to add something? Are we not wasting memory space?
Yes, we are, but that's the trade-off we have to make to create a dynamic array.
Okay.
Yeah, the trade-off we have to make. Everything is about trade-offs. If you are adding a functionality, you have to take something else. You have to reduce another functionality. Exactly. Space against time, correct. Space against time, yeah. So that's the thing, because if we don't do that, right, if we want to keep the space, that means we have to only copy what we need. But if we only copy what we need, when we need something else, we have to copy again to what we just need then. So if we keep copying each time we want to add something, it's not efficient. So the trick is, okay, if we want to copy something, let's copy as much as we can, so that the next time we are adding, we don't need to copy. It's kind of like if, how do I explain this now? So yeah, it's kind of like if you want to take a trip. If you have a line of people that are trying to travel from Lagos to Abuja, right? A plane doesn't leave each time someone comes. you aggregate things for people to move. So that is exactly the idea here. You are trying to add, you are trying to copy, not by a constant factor. You are trying to multiply by something. You can multiply by 2, you can multiply by 3, you can multiply by 4, it doesn't matter. But in this case, we just multiply by 2. So the reason why we are copying is because next time we want to add things, we don't want to have to copy again because copy is expensive. So we want to minimize our copies as much as possible. Yeah. So again, I'll go over this example again. Please follow this example clearly. So we have an array that is just one element. If we want to add 2, this array is filled up. So we need to copy to a new location that has space for 2 elements. So we do the copy here. How many copies did we do here? We copied 1 element here. Now I want to add 3. Sorry, now I want to add, so after we add 2, we want to add 3. But there's still no space in the array we have here. So we need to copy again. But because each time we copy, we double the array. We copy it to a location that is double, and then we add 3. So that when we add 4, we don't need to copy, we just add it directly. So if you noticed, we copied here 1 element, we copied here 2 elements. The next time we'll copy is when we add 4 elements, which is here. 5, 6. So we need to copy at 4 elements. We add 5, we add 6, we add 7. We don't need to copy. We need to copy at the 8 elements. Again. If you keep following, you notice that we need to copy at the first element, second, third, second, fourth, 8, 16, 32, 64. You notice that it just keeps going on like that. So if you take a summation of that series here, right? So let's say we add 16 elements. That means we copied. So if we added 16 elements, that means we copied at the first element. We copied at the second element. We didn't copy at the third element. We copied at the fourth element. Then we copied at the 8th element. So this is the amount of work we did due to copy, besides adding the elements themselves. So the amount of work that we did due to adding the elements is 16, which is n, which is our n in this case. The amount of work we did due to doubling adds up to n minus 1. That's the summation of this series here. And if you add n and n minus 1, you get 2n minus 1, which is O of n from the pattern last week. And if it takes us O of n work to add n elements, right, that means each add is O of n divided by n, because we need to divide by the number of elements we have, which is O of 1 on average. Is that clearer now? Thumbs up if it is, thumbs down if it's not. Okay, getting more thumbs up. I'm looking for thumbs down. I've not seen a thumbs down so far. Okay, so I'll assume this is clear. Okay, so the idea here that you need to take away is we are doubling each time we are copying because we don't want to copy each time. And that's what brings this down to O of 1. So it's something that we'll see as we go on in the course, but this is called the amortized cost. Being that sometimes we do an expensive operation so that we don't have to do an expensive operation other times to bring down the total cost of everything. So you can view the operations that are expensive as kind of sacrificing for the ones that are not expensive. Okay, so do we have any question here? This concept is very important, please, to understand. Any questions before we move forward? All right, so this is for arrays which have a fixed size. So this is for dynamic arrays. For dynamic arrays, copy arrays that have a fixed size under the hood. So they are managing a static array under the hood, but they create an illusion that they're dynamic, which is an abstraction. Yeah. So I guess how WSP is, but I'm trying to fully understand O of n. So it's O of n for the entire work. For the entire work, so to add 16 elements is O of n, not to add 1 element. To add 1 element is O of n divided by n, which is O of 1 on average. So O of n here is the work to add n elements. O of 1 is the work to add 1 element. Is that clear? on average, worst case. Worst case. That's an interesting one. So in this case, the worst case is O of n, yes. But we care about the average case. Because the worst case doesn't occur a lot of times. The worst case is very negligible. So if you add 1,000 elements, maybe the worst case will occur like 10 times. What about doubling? I don't understand the question. Please, if you want to ask a question, you can speak up and ask if because typing this in the chat doesn't give me a lot of context into what you're asking. Yeah, feel free to just ask.
Yeah,
speak up and ask.
I was the one who said that I understood the whole doubling thing, how it works. Or one thing, I don't think I've really understood the whole time complexity. And I was in the third class with books. I haven't really understood it. Yeah.
So, were you in the class last week?
Yes, I was in the class last week.
Okay. So last week we went over time complexities, and it's important to understand the time complexities in detail. I will suggest you go over those resources again and over the practice materials to try and understand why things are O of n, why they're O of n squared, why they're O of 1. But the reason why this is the reason behind the time complexities, you can look at it this way. You can look at it in a way of getting the total number of operations you are doing and dividing it by the number of elements you have. So in this case, the total number of operations we do, right, to add n elements is n. If you look at the total work we do, based on this analysis. So when you want to add elements, there are two things that can happen. You can either add the element directly, right? Or you can copy and add the elements. So if you add the element directly, that's O of 1. If you copy and add the elements, that's O of n and O of 1. Or O of whatever you have and O of 1. If that makes sense. So if we isolate those two components and say, okay, what is the amount of work to add the elements? We know that each time we add the elements, we have to do O of n, O of 1 work to add the elements. But sometimes we copy. How many times do we copy? Now, if you look at how many times we copy, right, we see that it's not every time we copy. And adding the n at the point we copy each time is what gives us this summation. Because you notice we copied the first time, we copied the second element. We don't copy to the fourth element. We don't copy to the eighth element. We won't copy to the 16th element if we go on like that. So adding this and adding it to the above gives us n into n plus n minus 1, which is 2n minus 1, which is still O of n. So that's how we get the time complexity here for adding n elements. Now, if we want to figure out how much it took us to add one element, we need to divide it by the number of elements we added, which is O of 1. But this is average, like someone mentioned earlier. The worst case is O of n, but the worst case doesn't appear too frequently. If you copy 1 million elements, the worst case can appear like maybe 10 times or 15 times. Essentially, the worst case will appear at the log of 2 to whatever you're copying. Because this is like a logarithmic sequence where you're doubling in a way. So that's why that's the whole time complexity. I hope this clarifies. Does this clarify or?
Yes.
Okay. But please, I encourage you to rewatch the first week. Those concepts are very important to move forward. Okay. So in a dynamic array, we have a concept of size and we have a concept of capacity. The size is the actual number of elements that we have in the array. The capacity is what you can hold. Because if you recall, when we double, we don't use up everything. There are still some spaces that we've not used up. So this distinction is important in a dynamic array because you notice that sometimes you have the size, in some languages, they distinguish between the size and the capacity. This is essentially what it is. Okay, so what you've explained, this is how lists in Python work. These are array lists in Java work. These are vectors in C++ work. And in JavaScript, these are arrays work. So essentially, anytime you have a dynamic array, what they are doing is they are managing a static array under the hood, and they are doing copying and they are doubling, or they are tripling. You could also triple. If you triple, you get the same thing. But as far as you are multiplying consistently and not just adding, you should be good. Okay, are we clear before we move forward? Our hands are reducing. People are getting tired. So please, if this is the first time you are getting this concept and it's so new to you, if you don't get everything now, it's fine. It takes time to understand sometimes. So you can go back and watch it again. But over time, in C#, I don't really know about C#, but I think it's similar to Java. I don't know what it's called in C#.
C#, we have array lists. We have some of them actually. Array lists is dynamic as well.
Yeah. So how does this doubly work in the real world application? You usually don't have to care about this really in reality. But for understanding algorithms and data structures, you need to care about it. Is static array deleted and replaced? I don't get that part. So the static array is copied to a new location. Now, whether that gets deleted or not is not really important. It might get deleted, it might not get deleted. But most times, if you are using a language that garbage collects, to delete it for you. If you are using C++, you have to go and delete it yourself. Because that can cause a memory leakage if you don't delete it. But usually, the languages will do that for you. Unless you're writing C. With C++, I think they have smart pointers now that do all these things for you. Okay, now, so when you're learning a data structure, why does this data structure exist? What is unique to the data structure? And what are the operations on the data structure? Because the fundamental thing we are trying to do is we are trying to store data and retrieve data. It's just that different data structures allow us to store data in different formats. And they allow us to retrieve them in different ways, with different time complexities. So what are the operations that we are doing on an array? So if you copy an array, we've gone over this before, it's O of n. Because looping through an array to copy it is O of n. If you append to the end of the array, we saw that analysis earlier. It's O of 1 to append to the end of a dynamic array. Amortized O of 1. Removing from the end too is easy. Just remove the element. You don't need to copy anything. Just remove it and leave that space open. It's still O of 1. Are we clear on these operations now? Before I move on to the next operations. Okay, good. You love to understand the mathematical parts. Yes, I can drop resources. I can drop resources later if you want to understand the mathematical parts. Yeah. So, if you want to insert at a position, that is not the end. So think about it. What do we need to do? Right. We want to insert at a position that is not the end. We need to create space for it by shifting all the other elements to the right, which is O of 1, which is O of n. So that's why the time complexity of inserting at position is O of n. The space complexity is O of 1 because when you are inserting, you are increasing the array by a constant factor. But it's tricky because if you insert sequentially, then it becomes O of n. But that's a different case. We are talking about one operation because I'm just inserting one thing. Now, the reason for this is that if you insert at a position, you need to shift the other elements to the right because they are stored together. You need to shift them. And if the array is, if it's a static array, you can't even insert into a static array because you can't shift it to the right because you don't know what is there. You need to copy it to a location that can take that. And when you copy the dynamic array, it doubles the size for you. At least double the size for you. To remove from a position is also O of n because if you remove from anywhere that is not the end, notice that if you remove from anywhere that is not the end, you need to do the same thing. When you remove it, you need to shift all the elements back. Now, if you remove it and you don't shift, it's O of 1. But if you remove the element and you shift it, it's O of n. Getting an item by index is O of 1. As we said earlier, as I explained earlier, where you can access any elements by the index. Are we all clear on this time complexities here? Please, if you are not, ask your questions. Yeah, please go ahead. Ifeanyi Chukwu, you have a question?
Sorry, I wanted to ask here, like, if we want to replace an element in the array, would it have a type complexity of O of 1 or O of n? And it's not,
so
it's not the end of the array.
So what do you mean by replace? What are you trying to do by replacing it?
So let's say I don't like I don't want the particular element that is at that particular place. I don't want it anymore. Like I want something else to replace it.
Okay. So there are two things you can do. You can set the index to something else that you want directly. In that case, it's O of 1. All right. But if you want to like remove it and shift all the other elements back, then it will be O of n. So it depends on what you mean by replace.
Replace by like I want something else to stay there, not the other elements in the array.
Then it's easy.
More,
Just
like the assignment.
Yeah, just like an assignment. So you just set the element at that index, which is O of 1. So getting and setting at an index is O of 1, as we saw earlier. Set item by index 2 is O of 1. So in that case, you are really setting the item at an index by doing your replace.
All right, thank you very much.
Yeah. Isioma, you have a question?
Yes, please. I would like to know about inserting an element in a certain position, right? So let's assume working with dynamic array, right? How do I know the number of spaces that are at the end of the array? Since to insert an element at a particular index, I have to move the other elements to the right. So how do I know the number of spaces that are at the end of the array, and then how many spaces to move the other element in order to create space for what I want to insert at a particular position?
So usually you don't have to worry about that. The dynamic array you are using would worry about that for you. But you need to know it to understand the time complexity. So usually if you want to, you don't need to worry about whether there's enough space or not. The dynamic array will handle that for you. But if from you using the array, you know the number of items in your array, you know the indices in your array, right? And if you are accessing an index that is at the end of your array, you know it's at the end. If you're accessing an index in the middle, you know it's in the middle. Does that clarify?
No, yeah, I get that. I get that. You know that it's not every time an element for dynamic array now and then going with what you've explained. It's not every time an element is added to an array that the size is doubled or tripled. Yeah. So I want to, well, I mean, I guess you've already said I don't want to have to worry about that, but I was just being curious to know how many spaces in the first place. Okay, was this array recently doubled or tripled? Just to know like how many spaces how many spaces forward I'll have to move the current elements in the array in order to create space for the element I want to insert at a particular position.
Oh, I see. So typically, your dynamic array will track your size of the array and to track your capacity. So it knows when the size is approaching the capacity and it doubles it. And it knows when you are trying to insert something and increases your size by 1 by shifting on the other elements as well. So those variables are tracked. In fact, as part of the practice exercises, I would you implement a dynamic array in your language. I understand this thing better when you implement it. So does that clarify?
Yeah.
Okay. I know. So if there are any questions you see how they're not clarified, please ask them in Slack. That way it's easier for us to go back and forth as much as possible. Please, I don't understand get item by index. So getting item by the index is essentially doing like A of 0 or A of 1. Let me give you an example of getting item by index. Maybe I didn't put this well in the slides. So So getting an item by an index is essentially doing like A0 or A1. Where is my slide here? Okay, so this is getting an item by index. Here, A0 is equals to 1. So if you access A0, it will return 1. If you access A1, it will return 2. Setting an item by index is assigning values to that index. So if you say A0 equals to 1, it will assign it to whatever you said. So that's getting and setting an item by index, which is O of 1. Does that clarify, Nancy? Mr. Emma, you have a question?
Yes. So about removing an element from an array, I want to ask, is it a crime or a blunder or bad logic to have an empty index? I'm asking because I want to know if I remove an element from an array, like I just remove it, I'm not putting it in another index. Would it be wrong or unacceptable to leave that index empty? Do I always have to shift like rearrange the array, like shift all the item elements to the right of what I just removed back to the left?
I see your question. So it's not, you could assign an element in an index to whatever type your array is holding. So if it's an integer, you can say, okay, maybe I'm going to assign it to 0 if I don't want to use that. It's up to you. But typically, you don't want to have holes in your array, because when you have holes in your array, you don't know what is in there. Like, you can't just have a hole in your array. It has to be initialized to some value, like some value somehow that's of the type you are storing. So you can do it that way. Sorry?
Is null not an acceptable value? Like, can't it be null? If I remove an element from an array, can't it have a value of null?
Yeah, it can be null, but then you can try to do something and then get a null pointer exception if you don't know that element at that index is null. So it's not good practice, but you can do it technically, but it's not very good practice. You don't want to have holes in your array. That's what I mean by holes in your array. When you have an element that is null, if you do it, they might have a null pointer exception, for instance, at one time, which is not helpful. So that's why it's usually when you remove elements, you usually shift it to remove those holes. Because the thing is, if you remove an element, right, you've removed it. You can't access that. You don't know that index unless you store the index you removed it from and know that is empty. But further down the program, you don't know which parts of the array are full or empty because you just have the address to the base of the array, to the start of the array. You don't know anything about what is inside. So it's not really a good practice, but technically it can be done. It also depends on your language again. That's why I'm talking in general terms here.
Thank you.
Yeah. So the shifts can happen. It can happen either ways, but typically it happens when you are adding stuff. So it can happen if you're adding and when you're removing. You can shift to the left and shift to the right. They're both two sides of the same coin. Can I sort an array? Yes, we talk about sorting data. Okay, so Ifeanyi Chukwu has a question.
Sorry, I just I don't know if it's off the topic, but when the question about shifts coming in and you said it can go both ways, is it that not like it needs like double linked lists, not an array?
So when we mean shift, we have an array, right? If we remove an item, if we take out an item, we need to shift all the elements to the left, that were to the right of the item to cover that hole that we left, right? Yeah. So we can shift. So that case, you are shifting backwards.
Oh, I get your point.
Yeah, but shifting forward, okay, I see your point. Shifting forward, so usually you shift backward. You shift to cover what you removed. Because if you want to shift forward, so you can also shift forward. Let's say I want to add an element into the middle of an array. I have to shift all the elements to the right, one step ahead, so that element can fit in. Exactly. So think about your operations in terms of, okay, what am I doing on the array and what is the time complexity? But generally, getting an item by index and setting an item by index is the fastest operation of an array. It's O of 1. Getting an item is O of 1. Setting an item 2 is also O of 1. Here. Now, if you are doing the operation at the end of the array, it's also O of 1. Because the reason why it's O of 1 is that you can easily do things to the end of the array without touching all the other elements of the array. But if you are doing any other operation, inside shifting anywhere that is not the end, it's O of n. So to delete an item is the same thing. When you remove an item, you have to shift all the other elements to cover up. Iteration is O of n because you need to go over the array. Finding an item is O of n. Now, because you can only get an item by the index. If you don't know the index of an item, you have to look through the entire array to find it. But this is where searching comes in. There's something called binary search. We'll talk about later. That makes it log n. If the array is sorted. If the array is not sorted, sorry, it's O of N. There's nothing you can do. There's no optimization. If the array is not sorted and looking for an item, it's O of N. There's nothing you can do. If it's sorted, you can use binary search. Now, if you have an array and you want to sort it, it takes you N log N to sort. So O of N to just find your item is better than sorting and finding the item with binary search. Okay, so other operations here, finding the mean of an array and finding the max. If it's not sorted, it's O of N, because you need to loop through to find the maximum element. I need to loop through everything to find the minimum element. So think about it like this. Any operation I do that has to do with me going through the entire array is O of N. If I have to go through half of the entire array, it's still O of N. Even if I'm going through some of them when I'm shifting, it's O of N. N over 1, N over 2, N over 3, N over 4 is O of N. So sorting depends on the algorithm you use. Some are O of N log N, some are O of N squared. We'll talk about sorting, I think, sometime later during the course. Getting the length of the array is O of 1. Now, this is funny because usually you should have to look through to count, right? But typically, because this is done a lot, those are stored as a variable to make things easier. So like in Java, I think you can do array.length. In Python, you can do length of the array. Different languages have their different ways of getting the length. So that's why they do it, because getting the length is important. So you don't have to count it and get the length. Because if you want to look through the array, you need to know how many items are in the array to set your index to look through. Okay, swap is another important operation. So swap means when you're taking two items in an array and you're swapping them with each other. So typically you have to use a temporary variable to store a copy. Some languages allow you to swap directly, like Python. But some other languages, you have to do it yourself. But swapping is O of 1, because what you are doing when you're swapping, you're accessing, you are getting an item and you're getting an item and you're accessing an item and you're accessing an item. So you just 4 O of 1 operations, which is O of 1. Getting the length of an array is O of 1, as we spoke about earlier. Oh, this is a duplicate. So are we clear on arrays? We are at the end of the arrays. I will also talk about the patterns later. But the key thing to take away is your dynamic arrays are okay. Someone has a question. Okay, maybe you were trying to do thumbs up. Okay. But the key thing to take away is static arrays, understand dynamic arrays, understand how arrays work, understand the time complexities of all the operations in the array. And when you're thinking of time complexity, think about what you are doing. How is getting the length of an array O of 1? So getting the length of an array is stored as a variable with the array for optimization. It should be O of N if you have to count everything. But because it's an operation that is done so often, most languages allow you to just store it. And if you're implementing your own, you just store it as well. So yeah, exactly. So that's why it's O of 1. Okay. So arrays and strings are the same thing. In fact, if you understand arrays, you understand strings. That's essentially why. Because a string is an array of characters. We talked about characters earlier. Now, a string is just an array of characters. So if you have a static array, so a string is an array of characters, usually a static array of characters. E.g., if you are storing happy, essentially this is how we store the memory. Now, there is this null indicator here. Now, the reason why this is stored is because strings generally don't have the length of the string. So sorry, I take that back. I take that back. Strings have the length of the string stored. But earlier on, when in the early days of programming, when they were using C and O, they needed a way to identify the end of the string without storing the length. So that's why you have this convention where you have /0 to know. So if you don't know the length of the string and you start here and you are looking through, if you see that element, you know that you're at the end of the string. But nowadays, you can store the length and you can make things easier. But again, don't care about this unless you're writing low-level C and C++. You don't really need to care about that. I just included it here for completeness. So strings and arrays are similar. So when they say a string is immutable, it means you can't change the string upon creation. And why can't you change the string upon creation? Because it's just a static array of characters. Some languages will say, okay, we support mutable strings. What they are doing is they are creating a dynamic array of characters. So once you get that distinction, it's easy to understand that, okay, this is what is really happening under the hood. So strings are immutable because they can't be changed once they are created. If they are using static arrays, mostly. I think C++ allows mutable strings. Yeah, C++ doesn't allow mutable strings here. So adding a character to a string is O of n. Because if you're adding a character to an array, normally we need to copy the array to a new location. Right? So it's the same thing with a string. If you want to add a character to a string, it's O of n because you have to copy that string to a new location. You create a different string. Now, this is important because it's easy for you to write an O of n squared algorithm thinking it's O of n. So if I have a string and I'm adding 5 characters, and I think, okay, I'm appending a character O of 1 times. If I'm appending a 5 characters and each character is taking O of n to append, that means I'm doing an O of n squared work. So what is the solution to this? So the idea here is different language, these things are language specific. But the general idea is when you want to work on a string, you convert it to a character array, right? A dynamic character array. Basically, add whatever I want to the dynamic character array and then convert it back to a string. Different languages have different ways they do this. The slides will be shared when we're done. So different languages have different ways they do this. Like I think with Java you can do to char array. With Python you can just do. I've forgotten how it is in Python, but different languages have how they do this. And some languages even make this easier for you by creating types that you can add to. You can build a string as you go, like string builder in Java. What string builder in Java does, essentially, it's using a dynamic array under the hood to build your strings instead of a static array. A dynamic array of characters. So basically, most languages provide a direct conversion from string to char arrays. So look this up in your language. It's important. We can't go over the languages. So some languages allow mutable strings. But then when they allow mutable strings, they're just using a dynamic array of characters. That's the thing. So if you think about a string as being an array of characters, that is like you've understood most of what you need to understand here. If someone have a question.
Okay. My question is, if we are looking at strings as arrays, how do we understand reassignment of a string, where a string can be reassigned to a different value, which could be longer or shorter in length? So if it's another string that is longer in length, I can say, okay, that's an O of n because we have to copy. In fact, it's a new array, but if it's a string now, if it's a different string that is shorter in length, maybe even 1 character, what would you say? Would that also be an O of n or O of 1?
Sorry, I don't get your question. So you have a longer string and you're making it a shorter string. Is that a question?
Yes, let me say I have a string happy and I want to reassign it to a single character.
So you want to shorten the string?
No, I'm reassigning it. I'm not shortening the string. Like maybe you can write a program where a string is a string has this value in this part of the program. But maybe because of an if condition, for example, and I say, oh, if this condition is met, then this is the value of this string. Meanwhile, it had a default value. Yeah.
I see what you mean.
So in that case, what would you say?
Okay, so I will try and explain this. So the thing is, when you create a string, strings are immutable generally. So once you create a string, right, it's created in memory, and that your variable is pointing to that string. Now, when you reassign a string, it creates a new string and points your old variable to the new string. That old string, right, is no more used and can be garbage collected if you're using a garbage collection language. Or you need to reclaim the space to prevent memory leaks. So essentially, that new string you are creating is a new string entirely. And you're just updating your variable to point to the new string. Does that clarify?
Yeah.
Okay.
I think it does. So the time complexity now will depend on the length of the new string that you are
correct.
That you
correct.
are creating. Okay.
Correct. Yeah. Stephen, you have a question.
Just a quick one. How does string builders work? In C# there is something called string builder. So instead of having a string, that have to you know maybe malleable at some point. Then you just create a string builder, and it accepts new strings. And how does that data type work? Because I don't see any difference between it and strings.
Okay, so a string builder is a dynamic array of characters. Remember how a dynamic array works, where the array is resized each time it hits a limit. That's essentially how string builders work. Instead of storing integers, they are storing characters. So under the hood is a dynamic array that it expands a static array and resizes a static array. So essentially, to be clear, it's a dynamic array, and a dynamic array essentially is a static array that gets copied and doubled each time we need to. That gets copied and doubled each time we copy. So that's how it works under the hood. Okay, cool. Yeah, so that's how anytime you hear mutable string, dynamic array under the hood. Immutable string, static character array under the hood. Okay. So before we go on, let me see. So generally, your time complexity for string are the same as arrays because they are arrays under the hood. So think about whether the operation you are doing requires a copy or not. And the question is someone asked earlier is very, very important. When you reassign a string, you are actually reassigning to a new string. So when you are creating new strings, you are creating a copy in memory. Like you are creating new strings in memory. So you can run into an O of n algorithm, O of n squared. Thinking is O of n. Because you are doing an operation in a for loop, for instance. And you think that each operation is O of 1. But then you are doing an O of n work with a string inside the for loop, which becomes O of n squared. Yeah. So I think we can move forward now. So are strings clear? Do we have any question on strings? Okay. So I'm going to go to patterns on arrays. I was hoping we'll be able to solve some problems, but I don't think we'll have time because our time is heading out. I was hoping we'll be able to do some problem solving. But generally, some patterns on arrays, you have 2 pointers, sliding window, 3 pointers, prefix sum. So these are ways you can solve. Let's solve. Okay, let's do this. Let me go over everything that we need to do. Then we'll come back to this if we need to solve. I will also just go over all the slides so that we'll cover everything we need to cover first. So these are patterns that I would come back to. So patterns of strings are the same as arrays, really. And there's an important pattern of strings called hashing, like using hash maps. But then we don't talk about hashing, so we'll talk about that later. So problem solving. So I'll come back to this. Let me just go through the exercises. So these exercises are what I wanted to go through first. So implement a dynamic array in the chosen language. Essentially, just implement a dynamic array. And you should have the following operations. So I put some operations there that you should support, and I put some tests you can use to test if it's working correctly. So implementing this will make you understand how dynamic arrays work under the hood. It makes you understand it perfectly. Then there's a LeetCode Learn card called Array 101. You can go through it and try and solve the problems there too. You can skip binary search. And you can skip binary search and use linear search instead because you've not done binary search. So if you have time, you can do this other Learn card. Sorry, this is a mistake. This should be arrays and string Learn card. This is a different Learn card. I will update it. But if you have time, you can do this. So some resources you can look at. So in my opinion, one of the best resources for understanding the patterns is this broken coding interview patterns. They have it for all the languages, but I don't think it's free though. That's the thing. It comes at a cost. But then there's LeetCode. LeetCode is like a website that solves questions and it groups them by patterns. And it also has video solutions to all the problems. So for visualizers, we have Visual Go. Like these are algorithm visualizers. So let me go through. So we might not need it this week, but these are things that help you to visualize algorithm and data structures. And then this is also a code visualizer. We'll use this next week, maybe next week or next 2 weeks when we are talking about data structures. Visualizing trees and graphs, they become handy. But you can go over them, play with them. This is a code visualizer here that allows you to, essentially you type in your code, and then it visualizes your code. So let me see. If I say A equals to 1, 2, 3, 4, 5, for instance, and I say, let me see. Okay, let me answer your code. If I say A equals to happy, and I say A equals to sad. So if I visualize this execution here, so it's happy, and then it's sad. So you can see that it gives you what it's like, kind of shows like what is happening in your code in a way. So this is like helps to visualize. You can do it in you have different languages. You have it for Java, C++, just to help you visualize what is happening. Educative has free trial for 7 days, I believe, which you can take advantage of to see if you like it. And then they also have 6 months for if you have a GitHub student account. Other than that, I don't think it's free. But it's a very good resource. This resource is one of the best resources I've ever gone through. This one, grokking coding patterns is very good. Because the key thing to understand is once you understand the data structure, now you need to think about the patterns and solve problems on them. And that comes with practice because you need to solve questions and look at the patterns that come up with these data structures. So these are additional videos and articles you can go over. So before we go back to problem solving, do we have any questions? Okay. So now this is where I'm at the midpoint now, because now I was hoping we'll be able to go through these problem solving things, but maybe we can maybe do 1 or 2, but I also understand that the time is up. So I think I'll leave it to the organizers at this point to make a call. Shay, what do you think?
Okay, so yeah, basically we don't have much time, but I believe we have some people here that are still interested, so I think we can go on. And for those that have something else to do, they can check the recordings later.
Okay, that sounds good by me. So we can always get recordings later. Okay, so I'm gonna go back to the problem solving and talk about some of these problems. Okay, so 1 second. I just need to get this ironed out. Okay. So the first pattern I'm going to go over is 2 pointers. So 2 pointers essentially are, let me, okay, so can you see my, why is it showing in this way? Oh, wait, something is wrong. Set to, share anything partially. Okay, I think I have to switch to, let's keep here. Okay, so, okay, I think, okay, so essentially when we have 2 pointers, we usually have an array like this, for instance. And then the basic fundamental thing we do on an array, right, is the basic fundamental thing we do on an array most times is to loop through the array. But then sometimes, instead of looping through the array multiple times, right, we can use 2 pointers to simplify the issue, to simplify what we're trying to do. So usually your pointers, sometimes it starts at the beginning. Oh, I'm not showing this screen here. Okay. So sometimes it starts at the beginning, sometimes it starts at the end. And then they come together. Sometimes they start at the beginning and one goes faster than the other. But the concept is you have multiple pointers in the array. So I'm going to take this question here. So I'll start with this one called reverse string. So essentially, this question is a discrete question essentially. And it says write a function that reverses a string. Is this big enough? Can you guys see clearly?
You can zoom it out.
What of now? Okay. So it says write a function that reverses a string. The input string is given as an array of characters. You must do this by modifying the input array in place, which all have one extra memory. Now, there's a reason why they give that constraint. And one thing I want to clarify is that when you read the question and understand the question first, because usually there are constraints with the question. They may give you a question and say, okay, the array is sorted. Every information they give you in the question is important. Because with that information, it may change the solution. So normally, if we want to reverse a string, right, given an array of characters, we can copy it to a new array, right, and go from back to front, filling up the new array. But they are saying we should do it in place without extra memory. And that is what makes the problem interesting. So just let's think about it, like what are the various ways? If you want to do this in place, what are we going to do? Like what are the ways we can do this? Like just brainstorming. Let's say we don't know what we want to do. One thing we could do is, okay, we need to reverse the string. That means we need to take the first element and put it in the last element. Right? And we can swap, correct? So we can swap the first and the last element. If we swap the first and the last element, what happens to the second element and the second to the last element? So think about it like this. If you have this string, right? If you take away the first and the last element, this is a new string, right? If you take away the first and last element, this is a new string. So you see that if you have a string and you take away a part of the string, it's still a string again of a smaller size. You see that? So that's one thing you should also take into consideration. Like when you are dealing with data structures, most of the data structures, they are recursive in nature. Meaning, if you take away a little part of them, they still form that same data structure as well. You see it with strings, you see it with trees, you see it with arrays. If you have an array, right, and you cut out one part of the array, the remaining part of the array is still an array. So whatever you did to the first part, you can do it to the second part. So if you swap the first and the last to give us a good solution, that means we can swap the second and the second to the last. You can swap the third and the third to the last, like that, till we get to the middle. So if you take this, for instance, now, just write it out. And let's say we have I here and we have J here. This is where 2 pointers come into play. So this is I here, this is J here. Like 2 pointers, 1 pointer at the beginning, 1 pointer at the end. If we swap these two, right, then we can increment I here and decrement J here. Oh, sorry, you can't see what I'm writing. Okay. So this is what I was talking about. So you have hello, right? You have I here and you have J here. I points to the first, J points to the last. That's why we call them 2 pointers, because you need 2 variables to go through the string. So if you swap these two, if you somehow swap these two here, right? And we have O here now. And we have, let me make this clear. So when we swap here, swapped, we have O here and we have H here. If we collapse and move in, and this becomes I and this becomes J, we can do the same operation and swap E and L. So we have E and we have L. We move I in here and we move J in here. Now, when do we swap? Do we continue swapping now, or do we stop? Now, If we swap one element, it's not a problem because we just swap the element itself, which is fine. But after this, now if we move I here and we move J here, should we still continue swapping? No, right? Because we've crossed. The elements have crossed. So we are going to do it until I and J cross each other. And that's essentially what, exactly. So that's essentially what 2 pointers is in this case. Now, for the code of it, I will leave you to look at it in your language, but I have an implementation I did in Python because Python is my go-to language for usually translation algorithms. And Python is my most complete language I'm most comfortable in. So I have a sample implementation here, Python. So this is the dynamic array I was talking about. This is my sample implementation. For dynamic array I talked about earlier on. But let's go to reversing the string. So this is essentially the solution here that I came up with. So what am I doing? I'm setting I to the beginning of the string. I'm setting J to the end of the string. This is how you get it in Python. Your language might be different. Then while I is less than or equal to J, I'm swapping. And then I'm incrementing I and I'm decrementing J. So this is essentially the solution to this problem. But I want you to understand why the solution works. And also to understand that as you are removing items from a string, you are getting a smaller string. And you keep doing it till you get one string. And that one string can be known as your base case. We'll talk about recursion later. So do we understand what I just said? Do we not? Thumbs up, thumbs down, thumbs up, thumbs down. Okay, perfect. Ms. Yoma, you have a question?
Please, I'd like to understand the base case. Like, when do we stop moving both pointers?
So in this case, we stop when the I and the J pointers cross each other. Because if we continue, we'll just undo what we did. And if we continue, we'll just undo what we did.
No, like,
so that is,
I'm looking at your while loop here.
Okay.
You said when I is less than or equal to J. So I'm trying to like visualize it. Maybe you could explain it to me.
1 second. I think this will help. Happy. This is my I and this is my J. So my J is the last element. Then, when I swap these two, I move I here. I increment I by 1 here, and I decrement J by 1 here. I swap. You see that it's the same thing we did earlier. We are doing it again. I swap. I increment I by 1, right? And I decrement J by 1 to come to this P. Now the trick here is, please, do you have a question? Please, can you mute your mic, please? Thank you. So the trick here is, it doesn't matter if we swap one element. If we swap an element, we still get the element. That's why we don't need to be checking if it's one element, if it's two elements. So do you understand how this algorithm works now?
So why is the question not when I is equal to J, like when they meet are like at the middle? Why will it also work when I is less than J?
It works when I is less than J. It works when I equals to J. The reason why it works when I equals to J is because if you swap an element with itself, you still have that element. That's why it works when I equals to J, because you are swapping an element with itself, which is still the same element. So essentially, yeah, that's why we can still do that. Otherwise, we could. I think it will work if we do it. If we don't even put equal to. If it's less than, it will work. If it's equal to, it will work as well. I believe it should work. Yeah. So let's experiment. Let's say we have. So the problem is we can either have an even element or an odd element. So when you are trying to test things like this, use a very small example. Don't use a big example. Like, okay, so let's use an example of, say, so an even element is ET. This is the smallest even element you can have, right? If I swap this, I'll get TE. So if I say I is here and J is here, when I do the swap, I'll get TE and then I will cross J. Like I will cross J. So we're good, right? If I have an odd element and I do the swap here, I will still cross J and we're good. So it doesn't matter if it's less than or if it's less than or equal to. It can only be less than or equal to if the number of elements is odd, if the length of the string is odd. So that one is fine. I believe it should be fine. Let me double check though. Let me copy this solution and see if it works. I think it should. It would work because I'll make it bigger later. What's happening? There should be a run button somewhere. So if I submit it, yeah, I think, okay, that works. Let me go back and see if I less than also works as well. Okay, that works. So it doesn't matter. It doesn't really matter. Yeah. Can you explain the last two lines in the code? You mean I plus equals to 1 and J minus equals to 1? So you are increasing I and you're decrementing J because I started from the front, J started from the back. So if you increase I, you have to reduce J. So I think in the code you are incrementing J as well. You are not decrementing J. Yeah. So that's essentially the key. So again, don't focus on my language implementation. Maybe there's a better way to implement it. It's fine. Focus on the algorithm, the concept, because your language might be different. Like when you are swapping in other languages, you have to use, like you did in JavaScript, you have to use a temporary variable. With Python, you can just swap on one line. So the time complexity here is, so let's think about it. What is the time complexity? Let's think about it. So what work are we doing? So in the worst case, what do we do in the worst case? In the worst case, right, we do n over 2 work because we start from either end of the string and come to the middle, which is n over 2. So it's still n work. It's O of n. So time complexity is O of n. You can only have a log of n if your array is sorted, or if you are dividing the input size by half each time. In this case, we are reducing the input size by 1 when we increment I and decrement J. So the input size is the size is reducing, but it's 1. It's by 1. So it's still O of n. Space complexity here is constant because we don't have extra space. Because we are actually using the space that was created. That's why they said do it in place. If we're creating, not live. So if we're creating a new string, then it will be O of n space complexity. But because we are using the same string, it's O of n, it's O of 1, because we are not adding, we are storing variables, but they are constant variables. Okay, so I think this is just a primer into two-pointer approach. Someone says if we have a check that looks to see if S of I, J, and in that case don't swap. Yes. Will it improve the time complexity? I don't think so. It will improve the time it will take to run the code, but it will not improve your time complexity. The reason is because you are reducing it by a constant factor by 1. That is just you're only reducing it by 1 swap. And if you have like 1 million elements, and it's only the last element you don't swap, it's inconsequential here. So that's why it doesn't really affect my complexity. Yeah, but it's an optimization. Yes, it improves the code. Yes, it improves the code. So that's for the first one. The other one I was looking at is two-sum. So two-sum is like a common problem. There are variations of the problem. But the reason why I took the problem is because it shows like a classic application of two pointers. Can you please explain why the time complexity is O of n? So it's O of n because you are going through half of the string. You have I at the left of the string, J at the right of the string. You collapse them in and they meet in the middle. That's n over 2, which is still n. Does that clarify? Okay. So for the two sum, this is a common problem. And the reason why I took it is because there are a lot of things, there are a lot of algorithmic techniques you can explore with two sum. But some of them we can't do now because we've not covered those topics. So I'll just focus on the ones that are applicable to two sum. But this question has like a lot of ways you can solve them. So the question says, given, let me make it bigger. So the question says, if you have a numbers that are already sorted, all right, we should find two numbers that add up to a specific target number. And we should return the indices of those numbers added by 1. So essentially, they're asking us to return the position of the number in the array. Like if it's the first element or the second element, which is why we add 1 to the indices. So do we understand the question? Thumbs up, do, thumbs down if you do. Oh, you're getting tired, okay. Okay, so essentially what they are saying is
what do they mean by one index? Does it mean that the array begins from 1 instead of from 0?
Yes, exactly. But you can ignore it. You can assume it's a 0 index array and just add 1 to whatever you want to return to make it easier. But what they mean by one index is yes, it's the array starts from 1 instead of 0. So they are saying it's sorted in non-decreasing order. All right, in non-decreasing order. What does that mean? Why did they say increasing order? Non-decreasing and increasing, are they the same thing? Well, almost. But increasing means it's strictly increasing. Non-decreasing means that it's you could have multiple elements that are the same. Exactly. That's why they say non-decreasing. Yep. So find two numbers such that they add to a specific target number. So let's look at this example here. You see the target is 9. So we are looking for two numbers in this array that sum up to this number. That is essentially what they're asking. But in this case, so they are telling us that let these numbers be numbers of index 1 and index 2. So the numbers are at index 1 and index 2 respectively. Where I is, so what they're essentially saying is that index 1 and index 2 is between 1 and the length of the array. So return the indices of the two numbers added by 1 because it's an one index array. That's why we're adding 1 there. So tests are generated that there's exactly one solution. You may not use the same element twice. And your solution must only use constant extra space. You see this limitation here. This is something we need to take into consideration. Because there are many ways to solve this problem. You can use extra space and solve it in a more efficient way. But I won't delve into that today because that has to do with using hash maps and hashing, which we've not covered. So do we understand the question now? Thumbs up, yes, thumbs down, no.
Yes.
Okay, perfect. Prince, you have a question?
Yeah, sorry, I didn't get that part. Reason why it's called non-decreasing order. So, like, you actually, the question was asked, why is it, or you really asked, why is it specified or sorted in non-decreasing order? So, like, why not increasing order? So, I really want to get that concept. Why use non-decreasing order instead of increasing order?
So the reason is, when you say something is increasing, if you have multi-duplicate elements, right, then that violates the principle. That violates that if you say it's increasing. Because you have multiple elements that are not increasing. So if I have 1, 2, 3, 3, 4, for instance, 3 and 3 are not increasing. They are the same. So that's why they are saying non-decreasing, because that satisfies that condition where you have multiple elements of the same type, where you have duplicate elements in the array. Let me try and, so can you see what I'm writing here? So if I say, let's say I have 1, 2, 3, 3, 4. Is this increasing? 3 and 3 is not increasing. So that's a problem. But if I have this and I say it's not decreasing, then it's correct. So essentially, it's because you can have multiple elements of the same type. That's why they're saying it's not decreasing. Yeah. So you can, it's kind of, you assume that, okay, but it's still increasing, right? Yes, it's increasing, but they like to be specific when they are describing things. Like generally, computer scientists and mathematicians, they like to be very specific in terms of describing things like this. So, okay, so let's try and see, okay, greater than or equals to, yeah. So what they mean is, yeah. So the equals to part is why they're saying non decreasing. If it's increasing, then it has to just be greater than or less than, however you look at it. So let me share my board here. So I want to kind of explain how you can approach this problem. Okay, so we have this, we have this, what's happening here? So we have this now, for instance, right? How can we approach this? We must use constant space. This is a requirement. So what we can do is, let's first think about this. How do we solve this normally? Like, if I'm trying to look for two numbers that sum up to this, what's the first thing that comes to mind? What is the first thing? It might not be the correct one. That's like the brute force solution. But what's the first thing that comes to mind? The first thing that comes to mind is, okay, so let's say I start from 2, right? If I just add all the numbers, all the numbers together. So if I start from 2 here and I loop through all these numbers, right, I might get my solution. So if I say 2 plus 7, 2 plus 11, 2 plus 15, then I have to go to 7 plus 11, 7 plus 15. You get the idea? So this is a brute force solution that works. It meets the requirement, it meets the constraint. But that will give us n squared time, yes, correct. But the reason why I put this is that it's important for you to be able to come up with this solution, even if you can't get the optimal solution. So let's just write what this would be. For instance, so if I say for, let me say, I'll be writing something that looks Pythonic because that's what I really know very well. So in range, say len of num, and I can say for j in range I plus 1, so len of num, right? I can say now if num of I plus num of j equals to my target, then I can return I plus 1 and j plus 1. Plus 1 is because of the 1 index. Normally, I should just return ij. I suppose you're not familiar with Python. Python allows you to return funny things, just to make things easy. But if you ask me, if you've not determined on the language you want to use to do interviews or for practicing algorithms, I would say Python is a very good language because it lets you focus on the main thing instead of like focusing on struggling with other things. So I can return ij if this is there. And if the answer is not there, then I can return whatever I want to return, maybe else, just an empty array or something. So this is a brute force solution. But if we analyze it, what is the work we are doing? Let's analyze this algorithm and see. So if we start I here, right, j goes through this entire array. Yeah, it's n squared time, but I want us to get the intuition as well. It's n squared time, yes. So j goes through this entire array. So what's the amount of work done? So the amount of work done here is what? It's n, right? Because n is the length of the array. Length of num. The amount of work done here is n because we're going from I to 1 to n. But the amount of work we do in this inner loop here, what is it? So we are using this dependent variable here, I, to loop to the end. So the first time, we'll loop n minus 1 times because we start from I plus 1 to the end. And if the end is n, and we're starting from I plus 1, and I starts from 0, that means the first time is n minus 1. The second time, we are adding 1 to I now, it becomes n minus 2. Third time, n minus 3. If we sum up this series up to 1, do you remember this pattern? This is summation of, this can be seen as summation of 1 to n minus 1, which is n minus 1 into n over 2, which is n squared. So I want us to understand this intuition because this pattern comes up a lot. Generally, this pattern comes up a lot where you have double for loops and you're not starting from the beginning of the for loop, you're starting from like that index. Now, if we modify this and said, okay, instead of starting from here, right? What if we wanted to start from the beginning? Let's say we didn't start from I plus 1. What are the things we have to take into consideration? So from here now, let me just write it out here so that it's clear. If I have I here, all right, and I start my j from here, we have a problem here because I can add this element twice. That means I can add the same element twice, right? I can add the same element twice. So we need to check. We need to add that check into our condition to make sure that the element is not the same. Something like if I is not equal to j, something like this. If I is not equal to j, then that will be a pure n squared time. Because we have, so I will go n times, and j will also go each one n times, which is pure n squared. But it doesn't matter even if it's n minus n squared over 2 over 3 is still n squared. So this is the brute force solution. Like this is just the brute force solution. Like just like if you just give the problem and give it to people, just solve it. How will you solve it? Exactly. Yeah, exactly. Num of I is not equal to num of j. So sometimes it's good to think about problems and think like, okay, if I didn't know anything about abstraction algorithms, how will I solve it? If you give me in numbers and you say I should determine which one adds up to this, then I'll just take them and start comparing them 2 by 2 till I find my answer. That's what I would just do. Just 2 by 2 comparison of everything till you find the answer. Essentially, so that's what we've just done here. Okay, so I think we can now go on to the more efficient solution. So I'm going to rewrite what we have here. Oops, sorry. 2, 7, 11, 15. And we're looking for 9. So now they told us that the array is sorted, right, in the question. So since the array is sorted, that gives us an inclination that there's something going on here. Now, sorted arrays make you able to find efficient solutions. Generally, they help you find efficient solutions. So how can we take advantage of the way the array is sorted? And the 2 pointers approach I will just learn. So let's say I have I here and I have j here at the beginning. Does that help us do anything? No, right? Okay. So let's say I have I and j at the end. How can I think about how 2 pointers can solve this kind of problem? It's not very obvious if you are first looking at it. But the key thing to note here is that you know that the solution is 2 numbers, right? Any 2 numbers. So let me try these 2 numbers. Say 15 and 2 is 17. Right. Now, Obviously, that's not a solution. But the problem now is, how can I move my pointers? Can I move I and J together?
No, I think you move one first.
Yes. Yes, because if I move I and J together, right, I will miss
an opportunity. Yes.
I'll miss opportunities. Yes. So the key thing to understand is when you have your pointers and you are moving, you try and make sure you are not eliminating any opportunity. And that as you are moving in a systematic way. Okay, so let's think about it. If you have 17 here, right? I know that this array is sorted. This is too big. This is too big, right? We need something smaller. Because the value you get is greater than the result. Exactly. We need something smaller. Now, it says we should move J. But why are we moving J? Why are we not moving I? Why not I? Why are we not moving J?
The list is sorted and our target is less than that. So we have to move left hand.
Correct. Yep. Because the idea here is that someone raised the hand, yes. Doms. Am I pronouncing it well?
Oh, yeah, sorry, teacher, I have to change my laptop to connect back.
Okay, that's fine.
I think putting a condition that filters out any number that is higher than the target would help. And then also maybe keeping one pointer constant and moving only one at a time. Like keep one pointer, maybe the pointer at the left constant while you keep moving the one at the right until you've looked through all the values in front of the first pointer before you now move the pointer on the left. Then keep it constant, then move the other one to ensure that each number is added with every other number. I don't know if that makes a lot of sense.
Yes, you are correct. Your solution is correct. It's correct. But the problem is, if I do that, that means if say I is 0, that means I'm going to move J to meet I, right? And that means I'm going to do n minus 1 work the first time. The second time, I will become 1. I'll move J to meet I. I'll do n minus 2 work. So by the time you add up the work you are doing, that becomes n squared. That's the problem with that approach. That's the problem with that approach. Yeah. Okay. So the thing is, when you have 2 pointers, you want to, if you look at the 2 pointers, there's one of several things that can happen. You either move both pointers or you move one pointer. Those are the 2 things that can happen. So now moving both pointers doesn't work. We are trying to move one pointer. Now we need to choose which one to move between the left and the right. But we know that what we have is greater than what we are looking for. Right? So we need something less. Right? And if we move 2 to 7, we are going higher. So we are going further than our solution space, the solution we are looking for. And because we know that it's sorted, we know that if we have 15, right, there's no other elements that will give us something closer to the answer. Like if we have 15 as one of the items, we know that 15 plus 7 and 15 plus 11 will not give us our answer. So we know that moving it, so we can eliminate all those conditions and just move back inwards. Because 11 is smaller than 15. So we might find an answer. So that's one thing you should also consider. Okay, when you're thinking, which side should I go? Try and eliminate the one that will not give you an answer. We know that moving left will not give us an answer because you're not going to go higher. Now we need to go smaller. Now, by doing that, we move J now. Here. Now we have 13. It's still too big, right? We need this smaller, not bigger. So we move in here. Now we have our answer 9. So with this now, yes. So the sum with time which pointer can you move? If it's greater, you move J. Else move I. Yes, correct. That is essentially the solution to the problem. So you can see here how going from the brute force helped us, give us insights into going into the correct solution. Yes, this is the best case, yes. because we have constant time and O of n time and constant space. And in this case, if you think about it, can we do better than O of n time? We really can't. Here, we can't do anything. Can't do better than O of n time, because what is better than O of n is log n, and there's no way we can eliminate half of the solution space you are looking for here. So in this case now, if we want to, I think I wrote the code here already. Let me just go through it. Yeah. So essentially, Python syntax. Setting I equals to 0, j equals to the end. We're looping through till it's less than or equal to. Why can't we move 2 pointers from the first and second indices in the beginning? Because if you do that, you have to, there's no efficient way to reduce it. When we did the first solution, that's what we did. We used 2 pointers at the beginning, I and j. We kept I here, right? And then we moved j to the end. For the second one, we kept I here. We moved j to the end. Third one, we kept I, we moved j to the end. So if we do that, we are not eliminating anything. We're just trying all different combinations we can find. And that's n squared, which is what we did first. If it's not sorted, the first solution would be better. So if it's not sorted, we can't do this. This solution will not work if it's not sorted. So this is not even a solution if it's not sorted. This is wrong if it's not sorted. So that solution is the only solution if it's sorted, if it's not sorted. But there are other ways you can do it if it's not sorted. But we've not talked about those things. You can use a hash map to make it easier. There are different other tricks you can do. But okay, let's even think about that. We have a solution, but let's just think generally, right? The crux of the matter is, if I have this array here, if I take this element, I want to search here if I can find the target, which is 9 minus 2. I want to search here. Now, because it's sorted, we can use binary search. We talk about binary search, but I don't want to mention it here. So we can keep this and use binary search on this to find if it's there or not. Oh, sorry, you can't see. Oh, so I've been showing, oh no, I've been showing my screen. Okay. So the first person that asked if you keep the 2 pointers at the same end, what I was trying to say is, if you have I here, right, and j is here, the only way we can do that is to move j to the end to find all possible combinations. Then we shift I in, we need to move j to the end as well. I move j to the end. So at the end of the day, it's still n squared. But what I was trying to say is, what we are trying to do is, if let's say we have 2 as I, we are trying to find in the remaining parts of the array, if you can find 9 minus 2. That's essentially what we're trying to do. But then, because it's sorted, we can use binary search to find. But we'll talk about binary search data. For now, we'll just keep it to this. Okay, so yeah, so if I is less than or equal to j, oh, someone already implemented it in JavaScript. Okay. So essentially this is the implementation here. Return I plus j, or so if this is the answer, return it. But if it's less than, I increment I. If it's greater than, else you decrement j. You can do it either ways, ji, whatever. But is this clear? Thumbs up, thumbs down. No thumbs up, so I assume it's not clear. Thumbs down if it's not clear. No thumbs up, no thumbs down. Okay, some thumbs up. Okay. I think folks are getting tired. Folks are getting tired. Yeah, I can see.
Please, can you, Shay, please, can you kindly explain this code block? Because that means that we have, after the if statement, when we have the life, I don't understand what that is. So can you just kindly go over the code block? Thank you.
Okay, I should explain this code block, right?
Yes. Thank you.
Okay, so what I'm essentially trying to do is that I'm trying to add 2 numbers at either end. If the 2 numbers are equal to my target, I have a solution, then I just return. Now, I don't know how familiar you are with Python. Maybe doing it in a language you are most familiar with to help. But if I add the two numbers and it's smaller than my target, remember what we said? We have to increment our sum, which is by moving I. Now, any other condition, you decrement J. Because at this case, it's obvious that numbers of I plus numbers of J is greater than 30. So the return is just to get back from the function. Like we found an answer, returning here. You just return the answer. Yeah. So does anybody still have any question on this? So that we can move on to the next pattern. I think we should move on to the next pattern if we are still going to do any other thing, so that we can cover as much pattern as possible. Is it not? Okay. Can we paint a scenario where the element that make up the target is not in the first index set? Of course. Let me see. Okay. Yeah, let's do something. 2, 3, 5, 7, 11.
You can see your
that is
screen.
not. Okay. So 2, 3, 5, 7, 11. Let's call it 1. And our target is 9. I think. So our target here is, what should we make our target? 12. Okay, let's make our target 12. Oh, so Python allows you to return. I'm essentially returning a list of 2 items, which contains the indices. So the returning I'm doing is, so essentially what she's asking is, here on this line, why am I doing this? So in Python, this is just returning the list, and the list has 2 items, which is I plus 1 and J plus 1. The reason why I'm adding plus 1 is because they said it's a 1 index array, so they want plus 1 in the answer. If not, there's no need to add plus 1. You can return same in JS. Okay, good. If you can do that in JavaScript, that's also good as well. So we are looking for what, 12, right? Let me go back to my last one. So we're looking for 12 here. So if we follow the algorithm, it's still the same thing. It's still the same thing we have. 11 plus 1. Oh, sorry, 12 is not a good one. Let me see. 12 is not good. Let me make this 0. This is better. So if I have 11 and 0, 11 and 0 is 11. 11 is less than 12, right? So what do? We need to move forward, right? So we move here. 14 here. 14 is greater than 12. So we need to decrement. So we move here. Move J inwards. I is here and J is here. 10 is less than 12. We need to increment. So we move I. And then 7 plus 5 is 12, our answer. So is this clear? Does it make sense? Perfect. Okay. Okay, so let me go back to my slides here. So sort array by parity, I think in this case, we can just talk over this. I may not need to write the solution. We just talk over what we are trying to do here. So essentially what it's saying is, if you have a number, move all the even integers at the beginning of the array followed by the other integers. So it's asking us to move all the even integers to the beginning and the odd integers to the end. So how can 2 pointers help us here? Any ideas? How can, yeah, go ahead, go for it, Jude.
With 2 pointers, you can start with one at the beginning. So, if our aim is to move the even to the beginning, we're going to use the swap. So we kind of like have a function that checks if it's even. If even, it's going to move to the given of like we're just going to swap it. So if the 2 pointers, like if the one that's at the end, if it is even, we take it to the front. Then if it is odd, we're going to take it to the back.
Okay. Yeah, nice. So he said we should. You are correct. That algorithm works. So if we say we should move it to the, he says we should move all even integers to the beginning, followed by the odd integers. So there are two ways we can do this. We can either move all the even integers to the beginning, or we can move all the odd integers to the end. That's our two approaches. So let's say we want to move the even integers to the beginning. How can we do this? So let's say we have 3, 1, 2, 4. How can we move the integers to the beginning?
We can't use.
Oh, okay. So how can we move the integers to the beginning if you have 3, 1, 2, 4? So we can have I here, and we have J here, looping through. So I and J, so we are moving the even to the beginning. So if 3 is even, right, it's odd. So it should not be at the beginning, right? It should be at the end. So in this case, there are two ways you could do it. We could put all the odd to the beginning, or the even to the beginning, or the odd to the end. So in this case, I want to put all the even to the beginning. So because it's not even, I just move my pointer forward. All right. Now this is not even. I move my pointer forward. You see what I'm trying to do here? It's just a pattern here. Now 2 is even. What do? I swap it. I will swap 2 and 3. So essentially, what I'm doing is I'm swapping all the even integers to the back. You can also do it and swap the odd integers to the front. It will work as well. Let me go through both approaches. So if I swap 2 and 3 here, right, I'll have 2 here, and I'll have 3 here. Sorry, 2 here, and I'll have 3 here. Then I can move my J forward. So when I swap, I move my I forward to point here because I use that index. And then I move J forward here. Then I can swap I and J again to give us 4 and 1. And then we have the answer. So that's the pattern for this. So I won't go into the code of this because of time. I think we are way out of time and I really want us to wrap it up. So I'll just talk about the other two patterns briefly. And then we can call it a day. We can continue with the stack chart if you want to, if you want more details. I can see folks are getting tired and numbers are reducing. Okay, so the other one we need to talk about is sliding window. So a sliding window essentially is when you have, you are going through the array a constant amount of times. And as you are moving, you are removing some elements from your search space. So in the resources, you can go over it to understand more about it and try and solve that problem. And then 3 pointers is a way of using 3 pointers instead of 2 pointers. It's a modification of using 2 pointers using 3 pointers instead. So essentially, you have 1 pointer at the back, you have 1 pointer at the end, then you have 1 pointer going through, and either swapping at the back and swapping in the front, depending on what condition is met. Yeah. So, I mean, there are lots of patterns, and I would highly encourage you to go through some of these materials here. I'll give you more patterns so you can play with each pattern and see the questions as well. So one last thing before we go out, I want to note is really on problem solving. So understand the problem, walk through examples, basic examples, simple examples, and then try and find a brute force solution. Even if you can't find the optimal solution, just find the brute force solution. Describe this time and space complexity, then try to optimize the brute force solution to get your optimal solution. So other hints I will give is go through a problem and try and solve it for like 10 to 15 minutes. If you can't, look at the hints. If you can't, then try again for 10 to 15 minutes. If you can't solve it after 30 to 40 minutes, look at the answer. So looking at the answer is not bad. It's fine. But just ensure you understand it completely. That's the most important thing. And you can use it in future. Like, ensure you understand why the answer works. That's the most important thing. So you understand why it works, the pattern that was used, and how that pattern can be used in future. Then solve it again on your own after looking at the answer. So the most important thing is to understand, to spend time thinking about it. But even if you are getting it or not getting it, but spending time thinking about it helps because that improves your problem solving skills. And these are some notes on problem solving that I just outlined there. You can just read them. They're just tips you can look at here. So I think we can call it a day. Any other questions before we call it a day?
Okay.
Link to
please,
yes.
Yeah, please. I saw the steps you itemized in problem solving, right? So thank you. I'm really glad I joined the session because I have to be sincere. I learned a lot, right? So looking at problem solving, right? So what I normally do, right, is that I first read through, then I try and write a pseudo code for it, right? Then I try and picture it, like, does it work? So recently, and a colleague was telling me that rather than looking at the answer, that one can try ChatGPT. So I don't know if that's a good approach, but he said it works for him. That yes, he said it does. That he has used it to, like, anytime he runs into like challenge, if he's trying to implement a feature in an application, that's what he does. So my own approach is I look at it, try and write it to the code. If it doesn't work, I refer myself to the documentation.
Yeah.
So I don't know, but I told him. Okay, go ahead. Let me hear from you.
So people have different approaches, but what I strongly suggest is try to solve it algorithmically before writing anything down. Before writing code, just try and solve it first. Just take a piece of paper, draw up an example, and try and see if it works first. If you solve it algorithmically, writing the code is going to be straightforward. You see, so there are two parts to problem solving. There is coding fluency, and there is algorithmic proficiency. Algorithmic proficiency is very important. Coding fluency too is important. Like being able to code is important. But academic proficiency is what to like really improve your problem solving skills a lot. And with regards to the ChatGPT having the answer, I think ChatGPT is fine if you look the answer. ChatGPT, as far as you understand what ChatGPT is giving you. I mean, I use ChatGPT a lot too. Like if I'm trying to do Stack Overflow or anything. It's okay to Google answers and find answers on the internet, but just make sure you understand what the answer is doing. That's the most important thing. Because ChatGPT will give you the answer. I don't know if you can ask it why I is equal to 0, why I is looking from the back or things like that. If you can ask it those questions and it gives you the answer, fine. But if it's just spitting out an answer for you, then you could have just Google it and find the answer as well. The same thing. So to solve it for you and give you the answer exactly. So it's getting the answer. The point I'm trying to make is that looking up the answer is not bad. The issue is when you don't understand the answer. That's where the problem is. But if you look up the answer, it's fine. And again, spending too much time on the problem too is really not helpful, because if you spend like hours and hours on the problem and you can't make inroads, then it's just this thing. He said when ChatGPT, when Mr. Shiki ChatGPT, who am I? Oh.
Thanks so much.
Yeah, that's fine.
So another thing I do is that about telling ChatGPT to explain. I asked him that, what does like the approach I tried it. I told it to like explain what that code block, what does it mean, and like line by line, it actually did. He told me why it was being used and why the approach works and those kind of stuff. Then he referred me to some materials. Rather than just copying the code and implementing it. Okay, let me see why does this work and why are we doing this way. Thank you so much.
Yeah, perfect. As far as you understand what ChatGPT is saying and ChatGPT is giving you the correct answer, the problem is if you also do your research and ChatGPT is not giving the correct answer, you have to also be careful, because ChatGPT sometimes it's learning, it's not always accurate. That's the other thing now.
If you go to bad or binge,
exactly. So it's still the same thing as Googling the answer. It's just that now it's just easier. It's just giving you the direct answer instead of giving you a page to filter for the answer. It's still the same thing. Yeah. So it's yeah. So what if the code doesn't agree? What if the code no agree you write after writing the pseudocode? So after writing, if you can write the pseudocode and it works, and you can't write the code, then that means the problem is code influencing. Then you have to know how to code in your language and understand how to bring data structures in your language. Can you show us your recommended resources again? They will share the slides with you. They will share the slides with you. Yeah. So I think that's everything we have here. Other than that, I think we should be, yeah. If nobody else, people still have questions, or are you trying to thumbs up? I assume you are just trying to thumbs up.
Hello,
Okay.
good evening.
Yeah, good evening.
Yeah, so I have a question, please.
Okay.
Okay, so I'm trying to like get an advice. Okay, if someone is learning data structure and you kind of like feel stuck and you are learning maybe array and string, for example, and you think you've not fully grasped what you are learning there, is it good to jump to another data structure, maybe Stack or something, or linked list, but you know fully well that you've not finished this one? Is it like, but it's taking longer or something? You're just there, you're just seeing some questions, you'll be like, what is this one again? So is it like you can move to another one and maybe in the future we'll keep learning other ones and referring back to them?
I see. So the thing is, as long as you understand the basics of the data structure, how it works, why it works, how to implement it in your language, from a learning perspective, you can move on to other data structures. If it's about not being able to solve questions without data structure, that's a different problem. Solving questions takes time to become very good at them. So I would say yes, learn the basics of data structure, understand it, and then you can move on to other data structures and come back to it. It's okay. Yeah, it's okay. But it's important to understand some fundamental ones, like arrays and linked lists. They are too fundamental. It's very critical to understand them. Yeah. Okay, so I think that's everything. So please, the feedback form is going out. Please, everybody endeavor to fill it and just give feedback, good, bad, everything. What do I think about using Kraken decoding interviews using Java? Yes, you can use Kraken decoding interview. Yes, it's a very good resource. If Java is your preferred language, then yeah, it's a good resource. Yeah, that's a good resource. But that's I would say if you are, depending on where you are, if you are more of a beginner, then the book might not be the best. You don't understand Java. So what language do you understand most? JavaScript. Then find a JavaScript resource. I don't recommend learning a new language because of interviews. But if you have to learn one, I would recommend learning Python. If you have to, but you don't need to. You can use whatever language you are. It's fine. You can use it for interviews. It's more about how fluent you are in that language. Okay, still have some questions. Let me see who's first. Jude. Okay, David. Someone asked okay, the hands have gone down. Is educative best for understanding DA? Educative is one of the best resources. Yes, they have data structures, they have patterns, and they have playgrounds with which you can walk through. I used to write Python for JavaScript in my new love. Good for you. Enjoy it. Let me see. So yeah, if we don't have any other questions, I guess we can.
Hello,
we can call it a day.
I have one more question.
Okay.
For the language thing, I was thinking, because when I started some few months or something, I think I use that because I work with Flutter. So that I don't know, that's not that fast when it comes to data structure and some things like that. So I don't know. So I think I was forced to learn JavaScript somehow because of the course I was using and educative or something. So because I was just trying to get an understanding when you say you can still use your language and things like that.
So that's the thing. I don't really know much about that, to be honest. I don't know much about data Flutter. I don't know, how good those languages are in terms of like the data structure and algorithm. So I can't really comment on them. But I would say, I think maybe you can check if you check lit code and you see people, if you check lit code and you see their solutions and you see people using that and Flutter, maybe it's good. But otherwise, I think JavaScript is a very good one because JavaScript is okay. Now there are some data structures you don't have in JavaScript that you have to work around. But other than that, it's perfect. It's fine. But I can't really speak too much to that and Flutter. I don't know how effectively. I've never used them before. Yeah. Okay. So thanks everybody. We've spent a lot more time than I expected, but yeah. Have a good evening, everyone.
Thank
So
you
thank you
very
so much.
much. Oh, thank you so much.
Thank you very
Please,
much. Thank
guys,
you.
don't
Thank you.
forget to fill out the feedback form. Thank you so much. And expect an email from me about the feedback form and other and the recording session and all. So thank you so much, everyone, and have a great night.
Yeah.
All right. Thank you.
Yeah. Bye, everyone.
Thank you so much,
Yeah, bye.
Shay. Thank you. Thank you. Thank you very, very much. Thank you to the organizers too.
Yeah, so for fishing out all these good ones.
Have a good night, everyone. Bye bye.